If Earth were a book, which page would humanity be reading? The question unclenches the mind like a key simple in shape, enormous in consequence. It asks someone to stand very still inside an enormous library and consider the weight of a single, fragile page between two fingers. It asks to imagine that every centimeter of rock beneath feet, every basin of ocean and shelf of ice, is not merely stone and water, but sentences and paragraphs, whole chapters written in a language of crystals and shells, of isotopes and grain sizes. Each layer is a line of text. Much of the text, however, has been rubbed away. This image is both comforting and terrifying. It comforts because it organizes chaos into something that can be read, learned from, and retold. It terrifies because it reveals how little of the original manuscript has survived the fingers of time. The planetary book is not a pristine library of continuous pages. It is a palimpsest, overwritten and scraped, leaves torn out and used for kindling. The forces that compose the narrative of Earth are not merely authors, they are erasers, editors, librarians who throw away whole chapters. To ask what page humankind has reached is to ask how much of the story remains legible at all. The first sensation that accompanies this question is vertigo. Geological time is not a long hallway, it is an abyss with its own seasons. A human lifetime is a punctuation mark, a comma, perhaps, in a sentence that stretches for hundreds of millions of years. When measured against rocks, a generation is the length of breath. Yet within that infinitesimal interval, human hands have rewritten lines with haste, cities have risen like annotations, machines have scrawled new symbols across the margins, and atmosphere itself has received a new flavoring, an ink of carbon that future readers will find impossible to ignore. If each stratum is a line, then whole formations are paragraphs. The Permian-Triassic extinction, the Cambrian explosion, the slow creep of ice sheets, these are chapters that shifted the grammar of life. Fossils are footnotes, isotopic anomalies are ink stains that tell of fires and floods and blooms of algae. A geologist reads this language with instruments and intuition, translating ratios and textures into past climates and vanished ecosystems. But translation is imperfect. The grammar of rocks is context-dependent. A limestone in one coordinate can mean a warm, shallow sea, while elsewhere a similar composition was written by a different hand entirely. The textual record is biased toward environments that accumulate and preserve information, quiet basins, sediments sheltered from storms, regions not swallowed by the churning maw of the mantle. And that is where the erasure happens. Plate tectonics is both chronicler and censor. Continental crust is born, folded, and sometimes consumed. Ocean floors are written over with new basalt and then erased where? They sink back into the earth. Mountains rise as epics and then slump into sedimentary footnotes. Rivers act like impatient secretaries, smudging ink and carrying away pages. Glaciers are slow razors, polishing and removing the identities of older surfaces. Even time itself has no mercy. Chemical weathering dissolves the mineral handwriting. Metamorphism transmutes phrases into symbols, recognizable only with special training. Consider the seafloor, older than 200 million years, almost entirely absent. It is as though the first half of a book were missing, and the reader had to reconstruct narrative arcs from the epigraphs left behind in surviving chapters. This is where curiosity wrestles with humility. If the planet keeps many of its secrets in the deep and the destroyed, then what confidence does humanity have in claiming to know the full sweep of the past? The fossil record is notoriously spotty. Certain organisms fossilize more readily than others, and soft-bodied life is often written as mere smudges. Large animals leave more obvious signatures, bones, burrows, and footprints, whereas entire ecosystems of small organisms and fragile filaments can disappear without a trace. The geological ledger is partial, and its silence can be deceptive. Yet within that partial ledger are clues that demand interpretation and, occasionally, challenge assumptions. Layers of black shale promise a sudden suffocation of oxygen. A band of iridium hints at an extraterrestrial insult. A change in sediment grain size tells of a storm that swept across a shelf and a geologic heartbeat. These are sentences from which entire theories grow. The human temptation is to stitch these lines into a continuous narrative and to imagine that they reveal a tidy chronology of ascent, decline, reinvention. The danger is to read certainty into ambiguity. Speculation, however, is part of the craft of reading. The thought that long-vanished civilizations, complex, sophisticated societies, might have arisen and been erased by the slow processes of geology is as ancient as curiosity itself. The planet has had long intervals of habitability and abundance, and the mechanisms of erasure are thorough. Erosion can wear down monuments until they are indistinguishable from bedrock. Subduction can swallow an entire continent's worth of architecture and culture, turning stories into nitrogen, oxygen, and silicon dissolved into the mantle's slow churn. Even if a civilization once left artifacts of stone and metal, those artifacts could transform, oxidize, or become buried under kilometers of subsequent deposits. The handwriting can be obliterated, but obliteration is rarely total. There are stubborn witnesses, mineral signatures that survive, isotopes that bear the chemical fingerprints of industrial processes, unusual concentrations of certain elements that do not typically occur naturally in their deposited contexts. The idea shapes itself into a speculative yet scientific question. What traces of a technological society would last through millions of years, and where would they appear in the stratigraphic sequence? The answers are not tidy, because the Earth does not preserve uniformly. Plastics, for instance, are durable on human timescales, but would degrade under the relentless chemistry of burial and heat. Radioisotopes created by nuclear activity leave distinct, measurable scars, but even those signatures diffuse and dilute. A plate of ceramic pottery might survive longer than a skyscraper because fiat clay is resistant to many forms of chemical assault, but pottery must escape erosion and burial to be found. From the vantage point of deep time, human artifacts may be marginalia, tiny corrections in a very large manuscript. Yet the mark they make is disproportionate in certain registers. The current era might be inscribed as a thin but unmistakable band in the sedimentary record. An enrichment of carbon isotopes from fossil fuel burning, a spike in metal concentrations from mining, a layer of plastic particulates mingled with pollen and ash. In some river deltas and sheltered basins where sediments accumulate quickly, the human signal could be preserved in recognizable stratigraphy. Elsewhere, continental recycling will erase the evidence entirely. The planet is a capricious archivist. Emotions arise when considering this. There is a small, sharp pride in the idea that humankind has written anything so distinct at all that in a mere blink, this species has altered the chemistry of the atmosphere, the composition of sediments, and the behavior of species worldwide. There is also a creeping dread. If much of what came before has been erased, perhaps much of what will come after will be unknown to us. A past silence is not merely absence. It is a mirror, reflecting the possibility that what humans produce now may vanish, understood by no future eyes, interpreted by no future minds. Thinking of Earth as a book invites a different kind of reading, one that balances forensic science with a literary sensibility. Geologists are both detectives and philologists. They look for syllables and grain-size distributions, for punctuation and abrupt unconformities, for metaphors and fossil assemblages that signal temperatures and salinities and the genetic innovations of life. They are patient readers because the book is written slowly. A layer a few centimeters thick might encapsulate thousands of years. In such a slow text, events that feel sudden to humans, an epidemic, a volcanic outburst, a rapid climate shift, appear as thin underlinings. Surprise is faint in the language of rocks. Yet surprise does occur, and the book occasionally reveals annotations that rewrite assumptions. Deep Time contains episodes of abrupt change, methane releases, ice house to greenhouse swings, and mass extinctions. These are the moments when the narrative tenses tighten and the page starts to smoke. They teach a wary humility to readers with only recently evolved attention spans. Humanity's own capacity to alter planetary systems sits squarely among such episodes, a potential agent of systemic change that may leave a recognizable layer. Whether that layer becomes a short-lived gloss or the framework for a new chapter depends not only on physics and chemistry, but on choices, on the rhythms of societies and the stewardship they practice. Another dimension of the metaphor is the comparative scale of script. Much of Earth's book is written in slow, flowing hand glacial striae, sediment drifts, coral growth rings, as if composed by patient monks. Human writing, conversely, is etched in the margins, sometimes in bold strokes. Cities alter albedo and water cycles, agriculture reshapes soils, roads cut linear scars across landscapes. These are not only physical changes, they are changes of narrative voice. When a species gains the power to redirect rivers, to accelerate erosion, to change atmospheric composition, the book literally changes the next line to be written. The geological record will carry that change forward, whether future readers interpret it as tragedy or triumph. The analogy extends also to what was never written. Before the first sediments were laid in a basin, there was nothing to record. Absence of sedimentary cover is silence, but silence can hide a wealth of action. Much of the planet's early history elapsed under conditions that left scant sedimentary residue. The oldest continental crust is fragmentary, like the first scratched pages of a manuscript. The reader must reconstruct from scraps, a zircon crystal here, a pillow basalt there, a tiny fossil fragment preserved against all odds. Specialists learn to hear meanings even in the faintest resonance. There is poetry hidden within the analytic detail. To think of a zircon, the size of a grain of sand-bearing isotopic memory of processes billions of years ago, is to imagine a single letter in the earliest sentences surviving through millennia of polishing and reforming. It suggests a humility in scientific interpretation. Sometimes an entire epoch must be inferred from a single durable grain. If humankind's ultimate legacy includes such grains, tracers that alter isotopic compositions in ways future geochemists can detect, then the species has written a micrograph that may outlast monuments. But the palimpsest also implies responsibility. If the Earth's record is fragile, then deliberate acts can leave enduring marks. Conversely, deliberate acts can also erase records of other beings. Humanity's rewriting might be accidental, the byproduct of energy extraction and consumption. Yet it is not inconceivable that some choices could be consciously made to preserve or mask evidence. The ethics of planetary stewardship thus extend into the archaeology of possibility. Will humanity be a caretaker who allows future readers to understand what transpired, or will it become an agent of erasure? This thought tightens into a question that will echo through subsequent chapters of inquiry. What kinds of archival strategies could guarantee that a signal endures into deep time? Natural processes offer some answers. Heavy, inert materials like certain ceramics, glasses, and metals can persist under burial conditions. Chemical markers, such as anomalous isotope ratios, can be recorded in sediments and in mineral precipitates. But the geological book is more interested in processes than intentions. It records changes in flux more readily than discrete artifacts. Thus, the most enduring human signature may be not artifacts, but altered geochemistry, the global fingerprint of combustion, of nitrogen fixation on a planetary scale, of species redistribution. Yet even here, ambiguity persists. When a future reader finds a thin global layer enriched in carbon-12 and depleted in oxygen-18, how will they distinguish the cause? Volcanism can do similar things. Biological blooms can too. Thus, the interpretive work remains. The more human signals overlap with natural variability, the harder they are to distinguish after long burial. This is a final twist in the book metaphor. The sharper and stranger the mark, the more likely it will be recognized. Subtle alterations are lost within background noise. Bold disruptions are legible. So if Earth is a book, humanity may be both marginal reader and clumsy scribe. The page upon which humanity reads is a thin one in a massive volume, yet the margin notes it appends could be unusually dark. The book's previous pages are missing in many places. Their absence both humbles and excites. It humbles because the incompleteness reminds human readers how partial their knowledge remains. It excites because every recovered fragment teases a story greater than current understanding, a story of environmental feedbacks, of biological innovations, of catastrophes and recoveries that surpass human timescales. The possibility, speculative but real, that entire cycles of complexity came and went, leaving only chemical footprints, beckons. With the thrill of archaeological discovery writ on geologic timescales. The narrator closes this opening thought with a final, quiet provocation. To read the Earth as a book is to accept that the act of reading may itself alter the text. By looking, by probing, by drilling and coring and measuring, humans leave marks. By acting, even with good intentions, they convert potential pages into preserved chapters or into erased scribbles. The question of which page humanity stands upon is thus not merely descriptive. It is normative. It asks not just where they are in the story, but what they will write next, and whether the pages that follow will be more legible than those already lost. For readers of deep time, that is the most intimate question of all. What will our handwriting look like to the future? What does a world look like before it learns to tell its story? Imagine a book whose first pages are blank, held open under an indifferent light, clean, without margin notes, without smudges. That is the image of the newborn Earth, a white book, not yet inscribed, a surface waiting for its first sentence. Those first sentences, when they come, are not written with ink and stylus, but with fire and water, violent, elemental, and irrevocable. From the haze of a protoplanetary disk, dust and ice coalesced. Tiny collisions, at first tentative, became a cascade. Pebbles clumped into boulders, boulders into planetesimals. and planetesimals into a mass large enough for gravity to begin writing its own punctuation. Kinetic energy folded in the heat. The young planet glowed. A molten envelope, no calm sea but a magma ocean, capped the nascent crust. This was the planet's opening paragraph, scrawled in incandescent letters, rivers of molten rock, fountains of vapor, the rhythmic thud of impacts rearranging sentences wholesale. Volcanic eruptions were the first handwriting. Lava streamed like calligraphy, flowing outward and then cooling into new pages. Each eruption was a stroke, sometimes a cursive flourish that broadened a continent, sometimes a blunt, blocky command that sealed a basin. These volcanic texts contained the elements that would later become the inks of life: carbon, nitrogen, sulfur carried from the deep by convective currents. The planet's core and mantle separated in a process of chemical editing. Heavy iron sank inward, forging a magnetic field that would later shield the document from some of the sun's harsher abrasions. That magnetic field was less of a sentence and more of a protective margin, invisible, vigilant, shaping what of the story would endure. Water arrived as both punctuation and revision. Some of it was trapped in the very minerals that accreted to form the planet. More arrived as gifts from the outer solar system, icy bodies that delivered their freight in energetic collisions. As the planet cooled, vapors condensed and rain began to fall. The first oceans were a new kind of literacy. Waves wrote ebbs and lines on juvenile shores. Tides, amplified by the moon's early closeness, traced repetitive margins across the rocky script. Water dissolved, transported and redeposited minerals. It carved channels that read like sentences across basalt and regolith and laid down sediment like a meticulous scribe smoothing a page. There was no calm in this early chapter. Bombardments, the steady punctuation of meteoroids and the occasional capital letter impact ripped new craters into the surface, rearranging and sometimes erasing the work that had just been set down. Each impact was a kind of editorial violence. Continents could be folded over, oceans boiled away, atmospheres thinned and thickened. The young Earth rehearsed its ability to both write and to destroy its writing, and that ambivalence became the defining quality of its record. Chemistry filled the blankness with possibilities. The early atmosphere was thick with carbon dioxide, nitrogen, water vapor, and trace compounds, an inkpot brimming with reactive ingredients. Lightning arced across heavy skies like a hurried pen. The energy of those discharges catalyzed new molecules, stitching together amino acids and simple organic structures from basic precursors. Hydrothermal vents on the ocean floor created a different kind of workshop. There, gradients of heat and chemistry produced disequilibriums, redox contrasts, and mineral surfaces rich and catalytic, metals that could promote the assembly of longer, more complex chains. In shallow tidal pools, evaporation concentrated molecules. In rock pores and clay flakes, surfaces arranged polymers in orderly rows. Each microenvironment was a laboratory, a scriptorium where chemistry rehearsed the possibility of poetry. The first indelible marks were not the brittle monuments one might expect. They were tiny, often microscopic, and their survival owed as much to stubborn chemistry as to circumstance. Zircon crystals, for example, mineral grains barely the size of sand, would later be read like dropped commas that nevertheless marked the presence of an author. Some zircons retain isotopic ratios and inclusions that whisper of conditions more than 4 billion years ago. They are the kind of single letter that outlives entire manuscripts, resilient, stoic, but also maddeningly brief. Their existence suggests that even in a world of convulsions and erasure, durability is possible in the smallest scales. This endurance is one of the paradoxes of planetary memory. Large structures, mountain chains, vast basins, even continents can be written and rewritten until the original script is unrecognizable. Smaller things, crystals, certain chemical signatures, peculiar isotopic anomalies may survive as relics. The early Earth's fossil record, such as it was, would be smudged and patchy. Soft, ephemeral phenomena left faint echoes rather than firm inscriptions. And yet, in a scattered handful of places, abundant enough conditions combined to produce the first readable traces of biology. Stromatolitic mats, layered accretions built by microbial communities, carbon isotope shifts indicative of life's particular metabolism, microfossil-like structures preserved within vein-laden rocks. They are the first sentences hinting at a life that could edit its environment. To read this infancy is to learn a new kind of humility. It is to stand before pages that are both incomprehensibly ancient and maddeningly thin. The Earth's early chapters are rich in violence and in possibility, but the very forces that allowed life to begin. Energetic impacts, volcanic outgassing, tectonic agitation also ensured that most of the earliest drafts would be overwritten. Plate tectonics would, in time, recycle crust into the mantle. Metamorphism would transmute sediments into denser, less informative rocks. Heat and pressure would blur handwriting into a homogeneous field of minerals. The palimpsest nature of the planet becomes evident. New text scraped across older lines, sometimes preserving fragments, sometimes erasing entirely. Yet the way these early processes arrange themselves is anything but random. There is a grammar to the chemistry and physics of a young planet. Redox gradients, for instance, produce predictable sequences of mineral precipitation. Iron oxides here, sulfides there. Where hydrothermal systems interface with seawater, minerals like pyrite can capture organic carbon and lock it away. In basins where sediments accumulated swiftly and anaerobic conditions prevailed, delicate organic matter could be buried before bacterial scavengers consumed it. These patches, sedimentary basins, buried deltas, calm lagoons are the places where the fragile script of early life had the best chance of being preserved. They are the archival pockets, the keystones of any paleontologist's dream. The drama of these early narratives carries an emotional charge that is subtle but profound. For the mind attuned to deep time, the image of a world learning to record itself elicits awe and an acute sense of scale. A human lifetime is scarcely a footnote. Human concerns are compressed into a typographical flourish on a page whose margins hold the accumulated weight of billions of years. There was a peculiar tenderness in noticing a single organic inclusion preserved within a mineral, and a corresponding terror in realizing how much has been lost to heat and pressure. The thirst to understand the beginning becomes simultaneously scientific and almost devotional. The search for the initial marks is a quest for origins that reads like a longing to witness the planet's first breath. This longing shapes the choice of methods scientists use to read those first pages. Rather than searching for skyscrapers of stone, the geochemist reaches for isotopic ratios, trace elements, and mineral inclusions. The sedimentologist studies grain sizes and layering like punctuation. Each lamination might indicate a seasonal cycle, a storm, or a sudden input. Geochronologists calibrate these sequences into dates, not as precise timestamps, but as relative placements in an enormous narrative. The techniques are forensic and literary at once, looking for phrase fragments, teasing meaning from context, and always treating the record as incomplete. It is tempting, and perhaps natural, to narrativize the early Earth as a linear sequence, a chapter of chaos followed by a chapter of stabilization and then the rise of life. But this is a simplification. The planet's infancy was episodic, bursts of violence punctuated by long, quieter intervals, moments of stasis that allowed complexity to accrete. Where the tectonic drumbeat slowed and sediments accumulated, stories could be told and preserved. Where the drumbeat grew loud again, through anerogenic uplift, through a cataclysmic impact, the narrative could be rewritten or torn out altogether. Even the forms that life took in these earliest readable moments were modest and cunning rather than grand. Microbial mats built layered carpets that trapped sediment and grew upward in very slow increments. Their preserved structures can be the first legible sentences of biology. Metabolic pathways etched isotopic biases into carbonate and organic carbon, subtle italicizations that later readers can detect. These early biosignatures are faint, but they carry the signature of directionality. Chemistry moved, processes shifted, and the planet's surface began to bear the mark of self-organizing systems. One of the deeper ironies of this primordial panorama is that the processes capable of producing complexity are also those that make the record so difficult to recover. Tectonic activity that helps to create diverse habitats, shallow shelves, volcanic islands, hydrothermal fields, also recycles and buries. Weathering that breaks down minerals to produce plant nutrition also smudges and carries away context. The consequence is a world where the very things that allow life to begin, the energy fluxes, the chemical disequilibria, also render its first testimony fragile. And into this fragile, vigorous infancy, the specter of erasure is always present. Imagine a beautiful paragraph smeared by rain, the wording muddied, some phrases irretrievably lost. That is the planetary record writ small. The implication is stark, even if some episodes of complexity, perhaps a brief flourish of novel ecologies, perhaps some technological-like transformation had occurred early on, the odds of their complete preservation are low. Instead, what survives are indirections, isotopic ratios, mineral assemblages, and the occasional stubborn crystal that refuses to rewrite itself. Those are the fossils of sentences, not the sentences themselves. The opening chapter of the Earth book therefore reads as both a promise and a warning. It promises possibility, the capacity for chemistry to self-organize, for gradients to produce complexity, for environments to become crucibles of novelty. It warns that the act of recording is tentative. The storyteller must accept that much will be lost, that the deepest breaths of origin may never be fully transcribed. To encounter the primordial panorama is to fall into a state of attentive suspense. The reader both revels in the beauty of incipient life and understands how tenuous every trace is. This tension between creation and erasure is not merely an academic point. It sets the terms for how later epochs will be read. The first lines, written in fire and water, establish the vocabulary of the planet, the components available, the forces active, the rhythms possible. They also establish the mechanisms of censorship. Anything written in those margins had to vie with heat, pressure, subduction, and erosion. The early Earth, in composing its first sentences, showed both the generosity of generative chemistry and the unforgiving hand of geological editing. So the reader closes the page of the planet's infancy with a compound sentiment. Wonder at the improbable confluence that allowed matter to converse with itself, and melancholy at the inevitable losses that followed. The white book is no longer pristine. It bears faint, smeared letters, first evidence of processes that will lead to life's longer tale, but many of its paragraphs are missing, torn from the spine. That sense of incompleteness will follow every inquiry into deep time. Yet it also fuels the work, to search for the few surviving letters, to reconstruct the threads, and to listen for the echoes of an early Earth that kept its first secrets in the interplay of fire and water. What does a chapter look like when a planet decides to write in basalt and salt water? When the book of Earth opens this time, the page is not a flat, polite sheet. It is a hot, wet surface that quivers, curls, and then hardens into text. The first lines of that page are written with lava rivers of fire that inscribe ridges and plains, and with water, the patient hand. That levels and collects, that smooths some sentences into quiet laminae and buries others under successive scripts. Mountains, seas, and continents are not merely features. They are the principal chapters of the planet's account. Each is composed by different hands, igneous fury, sedimentary patience, and tectonic stubbornness. Put together, they make a narrative of structure, a prose of rock whose grammar determines what will be legible and what will be lost. The image that comes to mind is literal and oddly domestic, a book whose pages have been folded, torn, scorched, stitched, and taped back together. A crease here marks a mountain range folded by collision. A tear is a missing span of time erased by non-deposition or erosion. A burn marks metamorphism, where heat and pressure rewrote mineralogy into a new alphabet. To open such a book is to confront the geography of editing itself. In the planet's youth, the magma ocean left a particular calligraphic residue. Where the incandescent mantle breached the surface, it wrote in thick, viscous strokes. Basalt flowed outward, cooled in skins, and then flowed again, building sheets that stack like pages. Along the margins, where magma cooled underwater, it produced pillow lavas, rounded, bulbous letters that look as if molten material were being exhaled into the cold of the sea. These pillows are the handwriting of a world that was still learning the balance between heat and water. Their texture betrays both violence and sudden calm, glassy rimes that froze the moment they touched seawater. Interior structures that hold vesicles of gas, bubbles that recall the rhetoric of release. Where lava met ocean with greater spectacle, steam roared and explosions scattered shards of volcanic glass. The contact zone became a crowded draft room, pillows and hyaloclastites and volcanic clastics piled together, and atop them, fine sediment settled as if to quiet the commotion. In these zones, the element of surprise lava contacting cold seawater left layers that read like abrupt paragraph breaks. Beneath the waves, hydrothermal systems set up a different kind of script. Hot, mineral-rich fluids vented from the sea floor, precipitating sulfides and oxides that would become the first chemical annotations of planetary processes. Those black smokers formed chimneys that captured metal-rich minerals and hosted nascent ecosystems, microbial communities that persisted in the shade of chemical energy rather than sunlight. The chimneys and their mineral precipitates are a form of fossilized marginalia, concentrated, local, and telling. The continents, as they emerged, behaved like chapters that demanded attention. Continental crust is compositionally distinct from oceanic crust. It is lighter, richer in silica, and more buoyant. It tends to remain at the surface longer, but the way continents come to be is itself a story of repetition and accretion. Volcanic arcs born above subduction zones add material to margins, terrains and microcontinents collide and weld together, and successive magmatic episodes build granitic roots that harden into shields. Early continental growth can be envisioned as the slow gluing of parchment scraps into a larger folio. Each accreted terrain is a scrap with its own local script, greenstone belts, banded iron formations, pillow basalts, that, when stitched to a proto-continent, adds a section of narrative that may survive for billions of years. Yet the very process that constructs continents also sows the seeds of their later erasure, mountain building. An orogeny occurs when plates converge and thickened crust is pushed skyward. Those folded mountains are textbook creases. Strata that were once horizontal are bent into anticlines and synclines, forced into tight loops and overturned packets. In those folds are layers of younger and older sediments, now juxtaposed in ways that resemble a page folded back over itself. The folding does more than create relief. It exposes deep rocks to the surface and to weathering. In a single sweep, a mountain chain can bring rocks that once recorded ocean floors into the light, only for rain and frost to strip them away. Mountain rivers act as erasers, removing rock and transporting it as sand and silt to distant basins where new layers are laid down. Thus, a mountain is both a chapter and an editor. It preserves a story in uplift, but also accelerates the circulation of pages into other chapters. Oceans, conversely, are patient archivists. Shelves and basins accumulate sediments with a kind of slow, faithful rhythm. In a protected basin, laminations can represent years, decades, or centuries of quiet deposition. In anoxic bottom waters, organic matter is less likely to be consumed and can be buried relatively intact. Black shales ore. Corrogenous beds can therefore act as high-fidelity registers of surface productivity and chemistry. River deltas are the bookbinders, where land-borne sediments pile up rapidly. They can entomb biologic and anthropogenic detritus in ways that enhance preservation. Rapid burial is a key word. Events like turbidity currents or sudden avalanches of sediment write thick chapters in the geologic. Heartbeat, preserving snapshots that are disproportionate to their brevity. Mid-ocean ridges, by contrast, are the presses that continuously print new pages of basaltic crust. Their output is steady and voluminous, an unending strip of fresh rock. But here lies a cruel irony. The oceanic pages are ephemeral. Plate tectonics is an active librarian that reuses vellum. As oceanic plates cool, subside, and eventually encounter a trench, they are bent and consumed back into the mantle, taking the printed sentences with them. This steady cycle means the seafloor older than some 200 million years is scarce. The consequence is that vast tracts of Earth's early chapters, written on the oceanic sheet, are missing from the surviving folio. Readers must reconstruct those parts from scattered marginal notes, slices of oceanic crust preserved in ophiolites, or chemical signals carried into continental sediments. Tectonic sutures are literal scars in the book. When an ocean closes and two continents collide, the intervening seafloor is scraped, folded, and sometimes plastered onto the edges of the continents. Those suture zones hold fragments of exotic crust pieces of ocean lithosphere, volcanic arcs, and sediments that are then welded into the larger volume. They are like pasted-in clippings, not originally part of the main narrative, but now essential to understanding the sequence. Within those clippings, the handwriting can vary wildly. High-pressure metamorphic rocks record deep burial and rapid exhumation. Blue schists and eclogites speak of high stress. High-temperature chapters, low-grade metapelletites, retain slivers of former sedimentary structure. The reader of joined continents must therefore navigate a collage of scripts. Unconformities are among the most dramatic editorial gestures in the planetary book. There are gaps missing pages where deposition halted, erosion removed what had been, and then new deposition resumed atop a scoured surface. Seen in cross-section, an unconformity is a visible pause in the narrative, a whole chapter excised and the text resumed with a different pen. Sometimes the missing interval spans millions of years. At other times it is a short but violent hiatus. Each unconformity poses a question to the interpreter. What was lost, and what does that loss imply? In a way, unconformities are confessionals. They signal that the book is incomplete in places, and that any reading must accept absence as part of the data. Glaciers are a type of mechanical editor that cuts and polishes in a distinctive style. As slow sheets of ice slide across bedrock, they grind and transport vast loads of rock and sediment. Striations on bedrock, polished pavements, and glacial erratics are like the deliberate smoothing of a page to erase earlier ink. But glaciers also drop their loads abruptly at their margins, moraine and outwash piling up chaotic chapters of unsorted detritus. The repeated advance and retreat of ice ages thus creates a palimpsest intimately connected to climate oscillation. The waxing and waning of ice writes recurring motifs across the landscape. All these processes, volcanism, sedimentation, accretion, collision, erosion, operate at different tempos. The distinction between a paragraph and a footnote in geological terms often depends on rate. A slowly accreting continental margin writes a long, steady chapter, a catastrophic event, a large impact. A pulse of volcanism puts in a sudden exclamation point that may be preserved as a thin but globally distributed layer. Yet the visibility of any event depends as much on the local context as on its magnitude. A massive volcanic outpouring will leave obvious traces where sediments are laid down in quick succession, but it can be invisible in regions dominated by later, more energetic reshaping. It is here, in the interplay of scale and context, that the metaphor of a folded, torn, scorched page becomes most useful. Some chapters, cratons and shields, are thick and palimpsested but stable. Their roots reach deep into the mantle and resist further rewriting. They house ancient rocks whose isotopic systems can be read to extract ages and conditions from Earth's early history. These are the oldest surviving folios, worn, annotated, but legible. Other chapters are thin and transient, ephemeral island arcs that rise and sink, continental margins that accrete and slough off. The durability of a given passage is not simply a function of age, but of structure and context. This geological structure frames what can be known and what must remain conjecture. The places that most reliably preserve narrative quiet basins and noxic shelves, rapid fluvial accumulations, are also the places where life's marginalia are most likely to be found. Conversely, the dynamic, high-energy province of mountain belts and oceanic trenches is a domain of both creation and erasure, where magnificent paragraphs are composed and then almost immediately cannibalized. The earth writes with different pens across its face, and a reader must learn to read each hand. There is an almost cinematic drama in watching these processes unfold, even in the mind's eye. One can picture a coastline where a volcanic arc rises, spewing ash that falls onto a calm sea. As the ash drifts, it becomes a thin but persistent marker horizon, a telltale line in later strata. Up the slope, rivers begin to drain the new land, carrying fragments of fresh volcanic glass into estuaries. Deltas form, burying those fragments and any organisms that lived through the initial eruption. Farther seaward, a black shale begins to accumulate in low oxygen waters, preserving organic carbon and perhaps the first hints of a chemical excursion. In time, a collisional event uplifts these sediments, and now they are subject to folding, fracturing, and metamorphism. The original horizon becomes a folded stripe, its original horizontality lost, but its composition hinting at the history of deposition and burial. Such a sequence is a single long scene in which many short paragraphs of the planet's book are written, rubbed, and then recomposed into a new script. The emotional tenor of these reflections is rooted in humility. To stand before a cross-section of folded strata or a cliff of stacked lava flows is to be made acutely aware of the fragility of any particular record. The planet's book is generous in some places and miserly in others. It offers up beautifully preserved chapters, those quiet, stable basins that accumulate and conserve, but it also delights in dramatic editing, often removing whole sequences with a single, inexorable mechanism. This is the double bind that shapes how humans can read the past. Great events might leave faint traces, and small, persistent processes might write entire chapters. Finally, there is an ethical undertone that links geological structure with human responsibility. The way chapters are formed and destroyed is indifferent to cognition or moral value, yet human actions now intersect with this ancient system of writing and erasing. Land use, mining, dam building, and coastal development modify sedimentary regimes. They change where and how sediments are delivered and buried. In altering erosion rates, humans are, in effect, choosing which local chapters will be preserved and which will be smudged. The geological book will accept these marks as any others. Some will become legible to a future interpreter. Many will be indistinguishable from natural variability. Atriality imparts a quiet, pressing question, one already hinted at on earlier pages. If the planet's chapters are so readily creased and torn, what will the next opening pages say about the species that now writes upon them? To read the mountain as a folded page, the ocean as a patient binder, and the continent as a chapter is to accept the landscape as both text and editor. It is to understand that the story of Earth's structure is not a sequence of static illustrations, but a dynamic, recursive process of composition and revision. The book opens and closes, folds and tears, and the attentive reader learns to cherish the legible fragments while always accounting for the spaces in between, the lost paragraphs, the erased lines that will forever complicate any narrative of origins and endings. What if climate were not merely the stage upon which life performed, but the ink that wrote the lines themselves? The thought shifts the reader's gaze. Mountains and basins are pages, tectonics, the hands that fold and tear them, but climate is the fluid that stains the parchment, sometimes a steady, pale wash that reveals detail, sometimes a thick, black blot that obliterates everything beneath. As a writing fluid, climate has a grammar and a temper. Its strokes can be delicate, seasonal laminations and thin peat seams, or they can be furious and inky, an extinction scale smear that changes the punctuation of life. Seen in the language of deep time, the planet's history is a series of editorial gestures by climate. Ice ages appear as compressed paragraphs. Their lines press close together. Greenhouse intervals are expansive. Looser-handed chapters. Desertification is a terse, arid marginal note that alters tone and texture. Each mode of climate produces a characteristic script on rock and sediment. The archive of Earth, therefore, depends as much on the nature of the ink as on the page it falls upon. Some inks last. Carbon buried in anoxic basins can be preserved for millions of years. Other inks fade quickly. Organic molecules exposed to oxygen and heat return to the vapor of atmosphere. What survives to be read is rarely the story as written. It is the story as written with indelible pigments. Consider ice, the most literal form of a cold ink. Glacial epochs write in a blunt, mechanical hand. Ice sheets advance like slow, unyielding erasers, rasping bedrock with a coarse script of striations, grooving and polishing surfaces until the previous handwriting is reduced to powder. They build tills, chaotic, unsorted dumps of boulders and mud that look messy to the eye but are specific to glacial conditions. In certain cases, ice can be preservative. Cold, anoxic conditions beneath ice can trap and mummify organic matter. Peatlands that form in permafrost can lock carbon away. For geologically meaningful intervals, ice caves and subglacial environments may entomb biological material and anthropogenic artifacts in a suspended state. Yet ice is migratory. Its preservation is provisional. Over millions of years, glaciers rearrange landscapes. They grind away horizons and redistribute sediment to distal basins. The net effect of glaciation on the geological record is paradoxical. It both destroys detail and creates coarse but unmistakable markers of cold. At the other pole of temperature, greenhouse climates lay down a different sort of handwriting. Warmer oceans reduce the solubility of oxygen. Stagnant basins can develop low oxygen conditions that preserve organic rich shales. Many of the planet's black shales pages dark with buried carbon date to greenhouse intervals. The warmth enhances weathering on continents, increasing nutrient flux to the oceans and fostering blooms that die and fall, sequestering carbon in sedimentary traps. Episodes such as the Paleocene-Eocene thermal maximum PETM leave a distinct isotopic fingerprint, a rapid negative excursion in 13C, a chemical scream that marks when a large pool of light carbon was injected into the system. That chemical signature becomes an indelible stain in the stratigraphic sequence. Yet greenhouse periods also accelerate chemical weathering and circulation. They can hasten diagenesis and metamorphism, transforming sediments into rocks that reveal less of the biological script. Deserts write in wind. Loess and Aeolian sandstones are the shorthand of arid climates. Vast, ancient deserts produce cross-bedded sandstones whose internal architecture betrays wind direction and the persistence of sand-moving conditions. But aridity is a double-edged pen. Dry environments are excellent at exposing older strata and therefore at making the planet's page visible. Yet they are indifferent to preserving organic matter. Bones bleach and crumble in the sun, soft tissues desiccate and are lost. The great expanses of Mesozoic deserts are often records of physical processes, dunes migrating, ephemeral wadis channeling water rather than biological inventories. In the same way, periglacial loess deposits, though formed by cold winds, often preserve pollen and microfossils that can be read as climatic shorthand. The texture of the ink differs. Wind-written pages tend to be coarse-grained records of physical environment with occasional fragile inserts of life. Between these extremes lie a universe of in-between inks, monsoonal rhythms that lay down rhythmic alternations of mud and sand, tidal flats that produce thin, high-frequency laminations resembling an almost musical notation, and anoxic basins that record episodes of oxygen collapse in chemical strata. Each climatic regime causes distinct sedimentary architectures and geochemical signatures. A tropical peat swamp will later be recognized by coal seams. A seasonally flooded delta will leave clastic sequences with paleosols and root traces. A prolonged drought will create a paleosol profile full of carbonate nodules and desiccation cracks. The planet, in its climate-inflected handwriting, leaves behind a mosaic of legible motifs for future readers. Yet climate does more than provide a depositional vocabulary. It is the agent that reshapes the distribution of preservable environments. Sea level changes driven by ice volume or thermal expansion rearrange coasts and shelves, translating depositional settings across space and time. A transgression drowns terrestrial environments, replacing them with offshore shales. A regression exposes continental shelves to erosion, removing previously deposited records. The same is true for precipitation. Increased rainfall in a region converts ephemeral streams into persistent rivers that carry and bury organic material. Aridification halts sedimentation and exposes surfaces to wind erosion, erasing the marginal notes of previous epochs. Where preservation happens, rapid burial in deltas, burial in anoxic basins, entombment under volcanic ash often depends on climatic circumstance. These dynamics create a fundamental asymmetry in the archive. Some climatic modes favor preservation of biological detail, others favor preservation of physical process. For example, an anoxic black shale may perfectly record a burst of algal production and preserve microscopic features of organisms, while a shallow, oxygenated carbonate platform might leave mostly skeletal fragments and few soft tissues. A rapidly prograding delta will trap and protect cultural or biological detritus, making it more likely to survive as buried material. Conversely, a landscape scoured by glaciers or desiccated by prolonged drought is a poor steward of delicate records. The result is that even if two eras are equally biologically rich, the one with depositional conditions favorable to preservation will dominate the long-term narrative. Climate extremes also drive evolutionary and ecological punctuation. Ice ages compress ranges, form refugia, and catalyze rapid speciation when barriers shift. Greenhouse epochs expand habitable zones poleward and can promote dispersal and radiation. Episodes of extreme aridity can fragment habitats, isolating populations and generating endemic lineages. The geological record therefore encodes both the physical fingerprint of climate and its biological consequences, turns of phrase, such as faunal turnover, extinction pulses, and radiations are all inscribed as the interplay between organism and ink. Mass extinctions are among the most dramatic manifestations of climate's editorial power. They are punctuation marks so forceful that they reset the vocabulary of life. The Permian-Triassic boundary records a cascade of changes: volcanic CO2 emissions, runaway greenhouse warming, ocean anoxia, that left chemical signatures, widespread carbonate dissolution, and a near-global biosilence. The end. Cretaceous leaves the iridium layer and shocked minerals of impact, and the subsequent cooling and darkness produce a recognizable sedimentary pause. In each case, climate acts both as cause and effect, a driver that triggers systemic collapse and a consequence that reconfigures depositional environments. The signatures these events leave are often global in extent and therefore legible even when local contexts are missing. Distinctive layers that act like bookmarks across the planetary folio. The interplay of climate with tectonics introduces another layer of complexity. Continental positions and mountain uplift influence atmospheric circulation patterns and oceanic gateways, which in turn affect climate. The closing of seaways can transform circulation and lead to regional drying or cooling. Uplift enhances weathering, drawing down atmospheric CO2 and potentially cooling the planet on multi-million-year timescales. Conversely, rapid seafloor spreading increases volcanic outgassing and CO2 levels, nudging the climate toward warmth. Thus, the hand that folds the paper also chooses the ink's gloss and color. The chapter that tells how plates assembled and rifted is inseparable from the chapter that reads how climates shifted in response. From a forensic perspective, climate leaves identifiable chemical signatures. Isotopic excursions, changes in C3C, Ca180, and other ratios are the fingerprints of shifts in carbon cycling, temperature, and hydrology. Sulfur isotopes can reveal oxygenation states of oceans, trace element anomalies, can point to increased weathering or volcanic input. Layered sequences of ash beds can be cross-matched across basins, providing synchronity and correlation. The most legible climate signals are those that are both global and abrupt: a spike in methane release, a bolide impact, a massive volcanic episode. These produce geochemical shouts in the stratigraphic record that are likely to be recognized by future interpreters. Yet there is mortal irony in this legibility. The most dramatic climatic events, those capable of producing global signatures, are also times when the planet's archive is most liable to be disturbed by erosion, reworking, and metamorphism. A cataclysmic volcanic pulse may splay tephra widely, but the concomitant uplift and erosion may later remove much of that record in certain regions. The PETM's isotopic signal persists, yes, but the biological details vary with depositional context. Tropical basins may preserve mollusks and foraminifera, while upland areas register only soil carbonates altered by weathering. The reader of deep time must therefore parse the simultaneous amplification and attenuation of clues. There is also a subtle ethical and existential resonance in treating climate as the ink of planetary history. If climate dictates what is preserved, then human interventions that alter climate are not merely ephemeral perturbations, but potential long-term edits to the geological narrative. The contemporary injection of isotopically light carbon into the atmosphere is, in geological terms, a bold brushstroke, unlikely to show as a negative 13C excursion in ocean sediments. Anthropogenic warming may shift precipitation patterns, destabilize permafrost, and lead to greater erosion in certain regions, thereby altering the spatial pattern of burial and exposure. In short, humanity is not only reading a page, but also contributing a new ink that future readers will have to decipher. Speculative questions emerge from this thought experiment without necessitating narration of particular actors. If a past episode of climate change erased a civilization-scale signature, where would evidence be most likely to survive? The answer lies where climate and depositional context favored preservation. Sediments that accumulated rapidly and were subsequently buried in anoxic, low-energy environments. Such places include deep basins, restricted marginal seas, and rapidly aggrading deltas. Conversely, periods of intense glaciation or desertification would have been poor at preserving technological detritus, though they might produce coarse macroscale markers, erosional unconformities, chemical shifts hinting at an abrupt, system-wide perturbation. The emotional tenor of this realization is both humbling and sobering. There is a kind of smallness embedded in the knowledge that entire floras and faunas can be swept away, their names reduced to isotopic blips or a thin black seam in a rock column. There is also urgency. Climate-driven processes determine which of today's artifacts and biosignatures will be legible to distant futures. As climate modulates the conditions of preservation, humanity's fingerprints may be preserved precisely where climate creates shelter-buried deltas, sediment-starved basins, or deep-sea fans, while elsewhere they will be blown away, chemically altered, or subducted into the mantle. Ultimately, to regard climate as ink is to accept a duality. The same forces that enable complex ecosystems and the proliferation of life also produce the modes of erasure that make the reading of deep time so partial. Ice and heat, drought and deluge, oxygen and anoxia, each is a stylistic choice of the planet. The archive is therefore not neutral, it is authored by process. Understanding the past requires translating not only the words left on the page, but also the methods by which those words were written and by which others were rubbed out. This awareness instructs a certain humility in the act of interpretation and an urgency in the act of stewardship. The pages the planet offers are precious and uneven. Climate will continue to be the ink, writing, smudging, enhancing, erasing. The task of those who read deep time is to learn the alphabet of those inks, to distinguish the deliberate strokes from the accidental stains, to detect the faintest letter forms in a smear of chemical change, and to recognize that the next paragraph written may be shaped by choices made now in a species brief moment between punctuation marks. What if the first readable letters in Earth's manuscript were not carved into stone at all, but grown folded membranes and filamentous threads that glowed faintly green under a shallow sun? Imagine the planet's first handwriting as a living script, mats and films that stitched sediment into layered columns, filaments that tracked silt and ooze, colonies that left behind domes and wrinkles like the braille of an emergent biology. This is the striking reversal of the common intuition that rocks tell the story and life merely occupies it. In the earliest chapters, life became the ink. The record of that living ink is subtle and often microscopic, but it is unmistakable once the reader learns the alphabet. Stromatolites, layered accretions formed by microbial communities are among the most eloquent paleographic forms. In shallow, sunlit waters, mats of microbes exuded sticky polymers, trapped grains, and precipitated carbonate, producing laminated domes that today read like sentences frozen in stone. Some of the oldest stromatolitic fabrics date back more than 3 billion years. In cross-section, they look like pages, thin laminae stacked with patient rhythm, interrupted occasionally by storm deposits or a change in chemistry. To the geologist who knows how to read them, they are the first signatures of self-organizing life, the earliest legible handwriting in the margins of a mineral book. Beneath the microscope, further sentences appear. Isotopic fractionations, the specific biases in the ratios of carbon isotopes, act as grammar marks. Biological processes prefer lighter carbon. When organisms metabolize and bury organic material, they leave a characteristic depletion of 13C in residual carbonates and organic matter. In rocks older than 3 billion years, pockets of carbon with this isotopic tilt are whispers of metabolism. Microfossil-like shapes, rounded coccoids, slender filaments appear in thin sections in cherts, sometimes contentious and ambiguous, but often persuasive enough to suggest that biology had already invented a basic lexicon: consume, reproduce, excrete, trap sediment. One of the most consequential phrases written by microbial communities came in green ink. Cyanobacteria. The blue-green photosynthesizers took the Earth's scattered chemical vocabulary and rewrote it into a new chemistry. Of atmosphere and oceans, where stromatolitic mats lay in sunlight, they photosynthesized, converting carbon dioxide and water into organic matter and liberating oxygen as a byproduct. At first, these liberated molecules were local, quickly mopped up by abundant reduced minerals and seawater and the crust. Iron dissolved in waves of an anoxic ocean reacted with nascent oxygen to form vast rust-colored layers, the banded iron formations, BIFs. These alternating strata of iron oxides and silica are among the most dramatic calligraphy in the Proterozoic folio, global, rhythmical, and chemically explicit. They are Earth's early marginalia that announce the gradual, episode oxygenation of the surface environment. That oxygenation was not a gentle edit, it was an upheaval. The rise of oxygen, the great oxidation event roughly 4 billion years ago, changed the chemistry of the planet on a planetary scale. Where oxygen accumulated, anaerobic metabolisms found their world altered. Methane concentrations probably fell, altering greenhouse forcing. Iron that had circulated freely in solution precipitated as rust, releasing nutrients and changing ocean chemistry. In rock, the effect is dramatic. Iron-rich bands give way to red beds, oxidized soils, and sulfide-poor horizons. Where once the page had been colored by reduced minerals and dark organic slurries, it now acquires new hues, paler carbonates, red beds, and oxidized surfaces. The planet's palette shifted, and with it the kinds of marks that would resist erosion and persist into the deep future. The emotional contour of this transformation is peculiar. On a geological scale, the photosynthetic act of cyanobacteria was at once modest and monumental. A metabolic pathway performed by microscopic organisms ended up altering the composition of an atmosphere, driving climatic feedbacks, and changing the rules by which future chapters could be written. There is an odd tenderness in imagining such small agents affecting such a systemic rewrite. There is also a quiet terror. The same biological innovation created conditions that were lethal to many of the planet's established residents. The great oxidation event becomes, in the narrative, both a composition and a culling, a turning point where the planet's text moved from anonymous sedimentation toward a document, co-authored by life itself. The Proterozoic world then unfurled a long plateau where life diversified slowly. Neural networks of biochemistry grew more complex, and new forms of cellular organization emerged. Eukaryotes, with internal compartments in mitochondria, appeared in this mise en scène, perhaps facilitated by the availability of oxygen and the energetic payoff of endosymbiosis. These cellular revolutions are reflected in chemical fossils, stearine and hopane biomarkers embedded in ancient rocks, molecular signatures that portray the presence of more complex membranes and metabolic repertoires. They are the punctuation marks that indicate new stylistic choices in the biological prose. As multicellularity emerged, first as simple aggregates and later as specialized tissue, life learned to exert influence beyond its binding role. Sheltering structures such as reefs began to arise in shallow seas, first built by microbial consortia and later by calcareous organisms. Reefs are architectural prose, three-dimensional constructions that capture light, influence currents and alter sedimentation. Where reefs proliferate, carbonate platforms expand, and those platforms create repositories where biological material may be entombed more faithfully. The biosphere increasingly became both scribe and archivist. Organisms modified environments in ways that enhanced the preservation of subsequent organisms' remains. Jumping forward across deep time, there is a chapter that reads like a sudden flourish of green ink laid thickly across many pages. In the late Paleozoic, vast swampy forests rose along equatorial lowlands, an aggregate of lycophytes, horsetails, ferns, pies, and primitive seed plants. To read these coal forests is to read the industrial-scale sequestration of carbon. Plant tissues accumulated in waterlogged peat, oxygen starved and preserved from decay. Over geologic time, that peat was buried and transformed into coal seams, the dark, dense strata that later became the fuel of industrial civilization itself. Coal seams are fossilized repositories of a world where vegetation dominated and where burial outpaced decay. They are literal chapters of green converted into black, and they appear in the stratigraphic record as thick seams that record both ecological abundance and a new type of long-lasting deposit. The proliferation of these swamp forests had planetary consequences. The burial of organic carbon drew down atmospheric carbon dioxide, allowing oxygen levels to climb. Estimates suggest that atmospheric oxygen during the Carboniferous may have been higher than today, enough that insects grew to extraordinary sizes and wildfires burned with ease. The biota was now not only influencing local sedimentary textures, but also reshaping atmospheric composition and climate. The handwriting of life had matured. It could now alter the ink's properties across the whole book. Once again, small processes, growth, death, burial scaled the planetary effects. Preservation during these green epochs was a matter of circumstance and accident. Rapid burial in deltaic complexes or under volcanic ash could protect delicate tissues and impressions. Peatlands, because of their anoxic, waterlogged state, preserved organic matter preferentially. Such depositional contexts are the archival niches of biosignatures. They are where the living script converts most cleanly into the fossil record. Conversely, tectonic uplift, erosion, and metamorphism could and did destroy countless chapters. The fossil record is thus patchy, not because life was rare, but because the conditions for writing and long-term preservation were. Spatially specific, there is a rich visual metaphor in the colors life left behind. Cyanobacteria stained shallow basins with subtle green and blue hues. Where oxygen precipitated iron, the oceans were striped with rusty red. Coal seams are black as dense ink, while carbonate platforms often appear as paler limestones, a sun-bleached parchment. Black shales, rich in buried organic carbon, are like pages splattered with bold pigment. Through deep time, the planet's strata change color as much as content, and those color shifts are themselves a readable script of shifting redox states, biological productivity, and depositional regime. To think of these layers as chromatic sentences is to appreciate how life's metabolic choices translated into a geologic palette. Life also authored a new kind of text, trace fossils. Rather than preserving body plans, many of the most legible ancient scripts consist of behavior burrows, tracks, feeding traces, and mat fabrics. These trace fossils are behavioral calligraphy, movements captured as structures in sediment. A worm's burrow disturbs lamination and becomes a preserved trace. A grazing trail across a microbial mat leaves a groove that, once lithified, tells of an animal's passage. Such traces are particularly valuable because they provide ecological information, how organisms interacted with their environment, rather than merely morphological similarity. Similarity! The first burrows and biotubation horizons marked a shift. Organisms were no longer passive recipients of sedimentary processes. They actively reworked their substrate, blurring lines between author and editor. From the standpoint of a future geologist reading deep time, particular biosignatures stand out as robust markers. Banded iron formations, black shales with negative carbon isotope excursions, coal seams, and certain fossil assemblages like the sudden appearance of skeletal carbonates or the Cambrian explosion of diverse body plans act as conspicuous typographical features. Biomarkers, molecular fossils such as hopenase and steranes, survive where morphology does not. They are the micro-ink traces that can betray the presence of particular metabolic pathways even when larger fossils have long been destroyed. These molecular fossils are prized because they can be pervasive and diagnostic, telling stories about ecological function rather than mere presence. All of this contributes to a larger, almost philosophical reflection. The biography of Earth is not simply a sequence of static illustrations, but a co-authored work where life became a feedback mechanism, both an agent of change and a recorder of change. Where microbes precipitated minerals, they created new horizons that future sediments would bury and remember. Where forests buried carbon, they changed atmospheric chemistry and therefore the climate conditions under which later pages would be written. Life began as marginalia and progressively took more of the main text. There is an emotional tone to recognizing life's agency in the sedimentary archive, a mixture of awe at the capacity for small-scale processes to produce profound global effects, and a humbled awareness of fragility, how readily those biosignatures may be erased. Entire ecologies, once widespread, can be reduced to a thin seam of black carbon or a scattered assemblage of root traces. A rise in oxygen that enabled complex life also precipitated extinctions of organismal lineages poorly adapted to the new chemistry. The narrative is therefore ambivalent. Biological innovation both made the Earth's story legible and, in many cases, made it more catastrophic for some of its actors. Ultimately, the earliest pages that Life wrote were decisive. They changed not only the content of the book, but its publishing conditions, the chemistry of the atmosphere, the composition of the oceans, and the kinds of deposits that would be likely to preserve future chapters. The living characters of cyanobacteria, microbial mats, swamp forests, and reef builders established a repertoire of marks, stomatal indices, and isotopic excursions, BIFs and coal seams, trace fossils and biomarkers that will be read and reinterpreted for as long as any archive remains. They are the first sentences written in green ink, later overlaid with rust and coal and chalk. As the planet moved onward, those first living letters set the stage for the more complex narratives to come. They taught a crucial lesson that life is not a passive inhabiting of a pre-existing story, but a force that can change the terms by which stories are told and preserved. The question is not simply what the book says, but who has been allowed to hold the pen. In the chapters that follow, that reflects the capacity of living systems to alter the record that will remember them will take. Forms stranger and more consequential still, writing with new inks, creating new textures, and producing signals that may outlive whole intelligences. The early biosphere, in its humble mat forms and towering fern groves, is therefore both preface and prologue. The moment when the planet first learned to write with life itself. What does it mean to stand in a dim, dust-thick reading room and open a book whose pages have been gnawed by time? The question uncloses itself, not as a mere curiosity, but as a moral and aesthetic interrogation. How does one appreciate a text when whole paragraphs have been ripped away, when the ink has faded into a ghostly suggestion of meaning? That image, an ancient volume with many torn pages and letters smudged to near illegibility, becomes a way to feel the rhythm of deep time. It shapes the aesthetic of understanding and the ache of incompletion. The Earth's record reads like that book, edges feathered, margins eaten, sentences half obliterated. The affect it stirs is double-edged admiration at the craft of preservation and sorrow at the irretrievable losses. The aesthetic mode of deep time is rhythm, not the predictable beat of a metronome, but a complex, layered cadence, slow crescendos of mountain building, staccato bursts of volcanism, whispered laminae of seasonal deposition, and the long, almost imperceptible diminuendo of chemical weathering. Each rhythm writes with a different nib. Pine laminations in a deep basin read like the practiced hand of a patient scribe, thin, repetitive lines that suggest seasons and years. Turbidite beds are the dramatic gestures, quick and forceful, burying chapters in an instant. Glacial striations grind whole paragraphs into powder, and massive impacts throw punctuation so fierce it reorganizes the book's architecture. The reader of this volume learns to listen to phrasing as much as to words, the cadence of deposition, the tempo of erosion, the syncopation of climate oscillations. Aesthetics in the geological sense is texture and grain, hue and patina. The pleasure of reading comes from the tactile imagination. The way a layer of silt feels like the faintest whisper of an ancient shore, the relief of ripple marks becoming fossilized. Handwriting, the gloss of a chilled basalt pillow that froze the moment it kissed cold seawater. Colors speak two banded iron formations as rusted calligraphy across a Proterozoic folio, coal seams as compressed ink, chalk as the pale underlining of prolific planktonic blooms. The palette is not merely decorative, it is semiotic. Each shade carries a history of chemistry, of redox states and biological flourish. To learn the palette is to begin to translate, but texture and color are not evenly distributed. The book's binder, The planet's tectonic and climatic systems has tended to preserve certain sections more faithfully than others. Quiet, sediment-starved basins become the vellum of high-fidelity chapters. Swamps and anoxic shelves act like careful archivists, sealing organic matter from oxidation and time. Conversely, mountainous creases and oceanic pages where the paper is thin and the hand of the editor is violent are places of loss. The aesthetic experience of reading such a book is therefore an exercise in selective reverence. To stand before a well-preserved section is to feel elation for the clarity it permits and grief for the missing context. That grief is an ethical feeling as much as an aesthetic one. Admiration for the fragments carries with it a bitter, steady regret. The mind recognizes artistry in the micrography, the preserved stromatolite laminations, the zircon's isotopic inscription, the exquisite Burgess-type soft-bodied impressions, but simultaneously knows that these are islands in an ocean of absence. The Earth's palimpsest does not merely obscure, it obliterates with an efficiency that can feel morally indifferent. Whole epics may be reduced to a single line of molecular residue. Civilizations imagined in speculative thought, if they existed, would be caught in the same economy of loss. A possible library burned to ash, leaving only a smudge of synthetically altered isotopes to hint at an intelligence that once annotated the margins. The theater metaphor deepens this sensibility. The planet, in this reading, is a stage where performance and erasure are intertwined. Scenes are set. Carbonate platforms, floodplains, hydrothermal gradients, then lit by forces of circumstance, sea level, orbital cycles, the interplay of tectonics. Acts begin with gradual exposition, slow accumulation of sediments, incremental diversification of life. Climactic acts arrive in sudden, often violent gestures, massive eruptions, asteroid impacts, abrupt climate excursions. The stagehands are indifferent. Physical processes, erosion pulls the curtains, rivers rearrange props, glaciers sweep away scenery. The audience is future readers, and their vantage point is inevitably partial. They will see only the props that survived and mistake stagecraft for entire narrative. Within this theater, certain sets are more generous in their offering. A delta that claims sediments swiftly provides the archival equivalent of a sealed stage box. Things buried there stand a higher chance of survival because burial is itself preservation. A deep, anoxic basin is like a darkened, controlled theater where the performance can be recorded with fidelity. In contrast, a high-energy shoreline is an open-air amphitheater where the audience must rely on fragments that have been blown or washed away. The aesthetics of preservation are thus intimately bound to dramaturgy. The more carefully and quickly a performance is buried, the more legible its record. This dramaturgical reading encourages attention to the micro-scenes as much as to the epic acts. A single stone-deposited bed can be an entire playlet, an intense interlude whose sudden burial captures a community in action. The lamination within stromatolites is likewise a sequence of innumerable small acts: growth, trapping, sedimentation performed rhythmically and preserved as a palimpsestic record. Each of these micro-scenes has its own tempo and aesthetic logic. The cumulative effect is a fragmented but still profoundly affecting narrative, where beauty emerges from scarcity and meaning accrues from the arrangement of scraps. Emotion arises from the act of reconstruction, when the reader assembles fragments, a carbon isotope anomaly, a thin ash layer, a smear of synthetic plastic microbeads within a paleogene clay. The mind experiences the twin sensations of revelation and limitation. Revelation is the cognitive thrill. A pattern emerges, a correlation clicks into place. The planetary handwriting resolves into a plausible sentence. Limitation is the bittersweet awareness that the sentence belongs to a paragraph whose key clauses are missing. That mixed affect admiration for the ingenuity of deduction married to regret for what cannot be known permeates the work of reading deep time. The aesthetics of fragments cultivates a particular kind of humility. Unlike an archive where every volume is intact, the planet's library asks readers to be connoisseurs of absence. They must learn to read negative space. Gaps and unconformities are as informative as the layers that anchor chronology. The ragged margins, where erosion has scoured and reworked, teach the reader to listen for the absent syllables. A polished bedrock with glacial striations suggests a whole set of earlier histories now gone. A veneer of weathered soil atop a buried horizon indicates a long hiatus, a punctuation mark whose content is lost. Elegance, in this context, is not only the clarity of an inscription, but also the eloquence with which the scholar acknowledges silence. There is also an aesthetic of scale that produces a peculiar emotional rhythm. Some clues are enormous and blunt. Global geochemical excursions, mass extinction horizons, clear exclamation points in the stratigraphic record. Others are microscopic, a trace metal anomaly, a molecular biomarker, a resistant glass bead with a manufactured alloy. The mind oscillates between awe at the planet-scale events and reverence for the tiny, persistent signs. The eye skates from a banded iron formation, an immense epoch-scale composition, to a single zircon grain whose lead isotopes whisper a story billions of years old. Both instill admiration, but for different reasons. One for the grandeur of planetary systems, the other for the tenacity of a solitary crystal that survived recrystallization and subduction. Regret, in such contemplations, has its own texture. It is neither passive melancholy nor acrid anger. It is a soft, penetrating ache for continuity. The reader imagines sequences in which causal links are missing. A sudden phono turnover with no obvious volcanic ash layer to tie it to a driver, a chemical anomaly unexplained by obvious mechanisms, a potential technosphere reduced to a faint isotopic perturbation that could plausibly be either natural or artificial. This ache carries an ethical dimension, an intuitive sense that stewardship of the present ought to account for what will be, legible in the ancient future. If the Book of Earth is the only remaining testimony of certain events, then the partiality of that book becomes a responsibility as much as a lament. Yet the experience is not only sorrow. There is a persistent aesthetic joy in the detective work, the patient collation of fragmentary evidence into a provisional narrative. It is the pleasure of pattern recognition and the satisfaction of an elegantly minimal hypothesis that explains multiple, disparate lines of evidence when a thin volcanic ash layer, a unique tephra geochemistry, and a distinct paleomagnetic reversal line up across basins. The moment resembles the relay of a play in which disparate scenes suddenly resolve into a single act. The beauty of that resolution is intensified by the knowledge that it was fragile and might have been lost. This aesthetic of fragile revelation shapes the modes of inquiry. Methods that amplify subtle signals, high-precision isotopic analysis, microscopic imaging, synchronity through tephrochronology become the tools of aesthetic reconstruction. They are the magnifying glasses of the reader in the dust-flecked reading room, allowing delicate letters to be discerned. The resulting prose is tentative, bracketed with uncertainties, yet it aspires to elegance, a concise, plausible reading of how events unfolded. Good interpretations read like careful translations of ancient, damaged scripts, sparing where the text is lacking, bold where the evidence is clear. The theater of Earth also performs an economy of erasure. Processes that conserve in one context destroy in another. Burial preserves, uplift exposes. Oxic conditions favor decay, anoxic traps yield preservation. The dramaturgy here is ruthless, an entire civilization, a vast floral assemblage, or a unique biogeochemical state might be perfectly documented in one sinkhole but utterly absent a few kilometers away. The aesthetics of such unevenness teach a critical lesson. Truth in deep time is often local. Generalizations risk mistaking a well-preserved vignette for a universal stage direction. Speculation about lost chapters, civilizations, or complex systems erased by geology inevitably rides on this grammar of preservation and loss. The mind frames possibilities. Where would an artifact survive for millions of years? Where would an anthropogenic isotope signature be locked into a stable mineral record? The imagination must obey the aesthetics of the archive. It knows that durable materials and rapid burial increase legibility, that anoxic basins and deep-sea fans are better than highland plateaus and glaciated valleys. This reflective constraint softens extravagant conjecture and grounds it in the tones and textures of known preservation pathways. At the heart of the aesthetic is a paradox that fuels emotion. The same processes that produce remarkable preservation also generate the conditions that lead to oblivion. Reefs, for example, are superb at building durable carbonate structures that can persist in the rock record. Yet the uplift that preserves those reefs may also expose them to erosion and metamorphism. Coal-forming swamps sequester carbon into seams that can last hundreds of millions of years. They also create landscapes that attract later exploitation and recycling. The reader of the Earth's book recognizes that beauty and loss are often intertwined, an aesthetic lesson about the fragility of testimony. Finally, there is a consoling humility in the acceptance of partiality. The reader learns to value fragments as carriers of profound significance. A single letter, an isotopic anomaly, a grain of synthetic glass, a unique distribution of microplastics can change interpretations and reframe narratives. The aesthetic pleasure of discovery is therefore not diminished by incompleteness, it is heightened. Each fragment, like a finely inked margin note in a torn folio, becomes precious precisely because it survived. The theater of the earth, then, is not a spectacle of omniscient clarity, but a staged sequence of provisional scenes, a choreography of appearance and disappearance. Its aesthetics are textured by rhythm, grain, and hue. Its emotional tenor mixes admiration with regret, its ethical subtext invites caution in how the present is written into future pages. To read this book is to practice reverence for what remains, empathy for what is lost, and a restless curiosity for what might still be found. There is beauty in the wounds and grace in the fragments, a poetic testament to the planet's tendency both to record and to forget. What does it mean in the ledger of deep time when the planet folds a landmass over itself and then tears it apart? What is the moral grammar of continents that assemble into great supercontinents only to be scattered again? That image, continents drawn together like glued pages and later peeling apart like brittle leaves, frames a central motion in Earth's long narrative, the continual making and unmaking of geography. It is a motion at once industrious and indifferent, constructive and censorious. The Earth writes chapters with mountain ranges and then, with an almost surgical patience, unwrites them through rift and subduction. The process has a name in geologic parlance, the Wilson cycle. It reads like the plot device of a planet with a stubborn rhythm. Ocean basins open, widen, then close, arcs of island chains accrete, collide, and weld into continental margins. Sediments accumulate in sheltered basins and later become the bones of uplifted ranges. Over spans of hundreds of millions of years, the planet cycles between assembly and dispersal. Supercontinents, sweeping assemblages of cratons and belts, appear as the boldest of editorial statements. Names like Nuna, Rodinia, Pangaea register as punctuation marks, episodes when the pages of the map were glued into a single sweeping folio. Between those moments, a different chapter was read, the one of dispersed continents and broad oceans, of shallow continental shelves and eperic seas that glittered and then vanished. The imagery invites a tone of awe. Imagine pages being sewn together, sutures and origins are the seams. When two continents converge, the intervening ocean plate dives beneath a contiguous lithosphere. The descent of that plate carries with it the physical evidence of ancient seafloors, ophiolitic scraps, basaltic naps, sediments that once lay beneath water, now plastered onto the continental margin. Those sutures are literal palimpsests, the place where older sheets have been pasted into the main volume. But the act of collision is violent. Rock is crushed, buried, heated, transformed. Sedimentary chapters that once recorded shallow seas and teeming shelves are folded into a mountain spine, their original horizontality contorted until the story appears in compressed, reworked fragments. A mountain chain is a long, complicated sentence in which clauses are smashed together and a new meaning, height, erosion potential, altered climate emerges from the compression. Then, on a different timescale, rifting tears those pages apart. Heat wells from beneath, lithosphere thins, faults propagate, rifts widen into linear seas, flood basalts coat the floors, and new oceanic crust forms at nascent mid-ocean ridges. The act of rifting is both a creative force, constructing new seafloor, opening spaces for life and sedimentation, and an erasing one. The thermal uplift and fracturing of a rifted margin expose older records to accelerated erosion. Rifted margins often host rapid sediment flux, and where deltas prograde into newly forming seas, they bury ephemeral quirks of biotic or chemical novelty. Yet these are fragile repositories. If the rift matures into a wide ocean, the seafloor itself begins a life of ephemeral youth. It will be recycled within a couple of 100 million years and most. Traces written upon it will be devoured. There is a certain cruelty in tectonic's stewardship of history. Oceanic crust is the planet's recyclable paper. It is continuously printed at ridges and, through plate motion, directed toward trenches where it is folded under and lost. The result is a biased library. The continental masses, cratons, shields are the most persistent folios. Their deep, buoyant roots render them resistant to subduction. They are the chapters most likely to survive billions of years, to preserve arcana such as ancient zircons or isotopic ratios that whisper of primordial processes. Yet even these long-lived volumes are periodically re-edited. Their margins are cannibalized, sediments scraped, and terrains accreted. The geography that seems immutable to a human lifetime is, in fact, provisional at geologic scale. This making and unmaking does more than reshape maps. It controls the conditions for what will be legible in the stratigraphic record. When oceans open, new shelves form and host rich ecosystems. When basins close, preservable sediments may be uplifted and subjected to oxidation, scavenging the very organic traces that would have made for a luminous fossil record. The site, timing, and mode of tectonic events dictate whether a moment in time becomes a fossilized clause or an erased possibility. Consider the fate of human handwriting metaphorically and literally under this machinery. Urban centers built on thick, rapidly accumulating deltas and coastal basins have a greater chance of entering the long-term sedimentary record. Layers of silt and mud, rapidly deposited, can entomb artifacts, organic molecules, and unusual chemical signatures before weathering and biodegradation convert them into aftertaste. A delta can act as a sealed envelope, a parcel of the present that may survive into the distant future. By contrast, settlements perched on uplifted plateaus destined for mountain belts are subject to erosion and may be ground down in the churn of orogeny before their signatures travel far from the memory of erosion. But tectonics is not simply a matter of physical relocation. It is a chemist and a climate engineer. Mountain building elevates rock to winds and rain, uplift accelerates weathering, and weathering is a long-term sink for atmospheric carbon dioxide. Over tens of millions of years, the growth of an orogen can draw down CO2 and nudge the planet toward cooler climates. Conversely, episodes of massive rifting and seafloor spreading increase volcanic outgassing, boosting atmospheric greenhouse gases and shifting the climate toward warmth. The assembly and dispersal of continents thus act as metagrammars of planetary change, constructing sentences in which climate, ocean chemistry, and biosphere composition interplay. Those sentences are sometimes abrupt. Rapid uplift exposes fresh rock, floods nutrient fluxes into oceans, and triggers blooms that alter carbon burial. At other times they are gradual, the quiet accretion of terrains that subtly reshape coastlines and biogeographic barriers. The openings and closings of seas are especially consequential for the preservation of signal. When a shallow sea expands across a continental interior, it deposits kilometers of sediment across lowlands. Ephemeral seas become long-lasting chapters in a basin's folio. These epiric seas can gather fine laminations, organic rich shales, and microbial mats, high-fidelity recorders of surface conditions. When that sea later retreats, the trapped sediments may harden into rock and be uplifted. If they survive metamorphism, they become windows into past ecologies. If instead they are later subducted or metamorphosed under high-grade conditions, the text becomes a homogeneous field of new mineralogy, legible only to those who know to read the altered isotopes. The planet's capacity to erase is remarkable in its comprehensiveness. Subduction is absolute in its consumption, metamorphism is transformative, erosion is relentless. An entire continental shelf's worth of cultural material cities, engineered landscapes, isotopic alterations to soils can be transferred into particulate form, carried seaward, and finally buried in a deep-sea fan where it might be smeared, diluted, and chemically reworked. Even the most robust artifacts, if they are not rapidly and deeply buried in accommodating sediments, will be slowly dismantled into their elemental constituents. Metal oxidizes and diffuses, ceramics break down under pressure and fluid flow, plastics fragment and eventually alter chemically. The geological process does not mourn these losses, it simply incorporates their atoms into new minerals. Yet the making and unmaking are not purely destructive. There is creation embedded in decay. Uplift exposes nutrients and creates varied topography, coastal shelves, valleys, basins, each of which becomes a crucible for biodiversity. Collision zones produce rain-shadow effects, new climates, and isolated refugia where evolution can perform its slow experiments. Erosion redistributes sediment, building new deltas and filling basins that will be the archival pockets of distant futures. The very destruction of mountains is the creation of sedimentary plains that can be fertile sites for life and, in exceptional cases, for long-term burial of organic or technological signatures. The interplay is necessary. Without rifting, there would be no seafloor spreading. Without subduction, there would be no recycling of volatiles that sustain mantle chemistry and drive volcanism. The planet's editorial process is thus both cruel and generous, cutting away and assembling parts to produce landscapes that alternate between hospitable and hostile, visceral and barren. An observer reading the record across multiple cycles discerns patterns, Large igneous provinces, vast outpourings of basalt, often correlate with periods of environmental stress. Continental breakup can produce flood basalts that flood vast areas, alter global climate, and leave behind marker beds that are gross and visible across many basins. Conversely, the slow quiet of a craton interior can preserve delicate microfossils and biomarkers that would not survive in an active margin. The geologic truth is always contextual. The same biological event can be presented to the future in drastically different ways, depending on whether it fell within a closed basin or an uplifted peneplain. There is also a profound lesson about contingency and chance. The fates of archives are spatially capricious. Two sites lying a few kilometers apart could have dramatically different longevity depending on tectonic fate. One may be buried under sediment and sealed for eons, the other uplifted and stripped of any record. Thus, when the planet's book is read, the sample of pages that remain is inherently biased. The surviving narrative is not a faithful copy of the past so much as a curated anthology shaped by tectonics, climate, and luck. Emotionally, this splicing of creation and decay evokes a mixture of humility and urgency. To imagine continents colliding and then dissolving underlines the smallness of human projects in geologic time. Yet there is also an urgency in the recognition that what humanity chooses to bury or to leave exposed may determine whether its traces are legible millions of years hence. The same forces that erase humans' handiwork will erase entire empires of geology. Coastlines will prograde and retreat. Deltas will sink. Oceans will open and close. The preservation of a signature is therefore not simply a function of its uniqueness, but of the accident of where and when it fell into the sedimentary conveyor. From the vantage point of speculative forensics, one might ask, where do tectonics favor preservation of a rare signal? The answer is, predictably, where burial is rapid, subsequent heat and pressure are low, and oxygen is excluded. Restrictive basins, rapidly prograding deltas, evaporitic basins, and deep-sea fans are the repositories most likely to lock a moment in place. Conversely, mountain-building provinces, active margins subject to frequent uplift and metamorphism, and old seafloors that will be consumed by trenches are the least reliable libraries. Tectonics thus prescribes an archival geography, pockets of memory embedded within a vast apparatus of forgetting. Finally, the planet's habit of writing and then re-editing creates a narrative ethic for the reader of deep time. The Earth's archive is not impartial. It is the product of processes that favor certain voices and silence others. To understand the past is to account for those biases, to read the absences as carefully as the presences, and to admit a humility in any grand reconstruction. Each mountain range, each rift valley, each closing sea is both a testament and a question. The continents that merge and split are not merely cartographic curiosities. They are the author's hand, setting down and then erasing clauses in a story too vast to be told without omissions. In that sense, creation and decay are not opposites, but co-authors. The Earth constructs archives and then, through the same motions, prepares the conditions by which they will be transformed. The reader of that book, patient and provisional, learns to recognize the seams and margins, to follow the grammar of uplift and subsidence, and to translate a text written in rock into the sweep of planetary life. The pages will continue to be sewn together and torn apart, and the planet will continue to write and edit, sometimes with violent flourishes, sometimes with a patient hand. The persistent lesson is both modest and stark. What endures is shaped as much by the craft of construction as by the mechanism of decay. What if every living thing were simultaneously a sentence and an editor? That image, life as both text and typographer, frames the realization that the biosphere does not simply occupy Earth's pages. It reshapes the punctuation, smudges margins, and sometimes tears out whole paragraphs. In the long ledger of the planet, each evolutionary edit ripples outward. A new lineage appears, carving a fresh phrase into ecosystems. An old lineage vanishes, its letters flaked away by weather, eaten by microbes or dissolved into seawater. The interplay of biology and climate is not a gentle correspondence, but an accumulated choreography of cause and effect. Organisms change environments. Environments feed back to select which organisms persist. The Book of Earth is authored by these recursive edits. The simplest examples are almost mundane and therefore revealing. The colonization of land by photosynthetic organisms, first microbial mats, then lichens, and finally forests, was a cascade of editorial choices. Where naked rock met the first filamentous life, chemical weathering accelerated. Microbial films trapped dust. lichen acids dissolved mineral surfaces, root networks bound soil. Those processes altered runoff chemistry and increased the flux of silica, phosphorus, and cations into rivers and ultimately the ocean. With increased weathering came increased burial of organic carbon and shifts in carbon dioxide concentrations. Atmosphere and climate responded. In the Devonian and Carboniferous, the emergence and spread of deep-rooted vascular plants transformed continental surfaces into much more efficient sinks for carbon. The result was more than a botanical flourish. It was a systemic rewrite that helped draw down CO2, modified hydrology, and fostered cooler glacial episodes. The appearance of forests was an editorial stroke that reworded the climate chapter for millions of years. At sea, tiny architects accumulated their own edits. Microscopic plankton, coccolithophores, foraminifera, and myriad calcareous nanoplankton bury their skeletons by the billions. Over geologic time, those accumulations became vast carbonate deposits, chalks, limestones, and platform carbonates. Each bloom is a page of deposition, each burial event a preservation of a phrase. The chemistry of the oceans depends upon these writers. When calcifying plankton dominate, alkalinity and carbonate saturation increase, influencing how the ocean sequesters carbon. When blooms die and sink in oxygen-poor waters, they create black shales and organic-rich horizons, locking carbon away on timescales that matter to climate. Tiny changes in marine primary production, changes that may be driven by nutrient pulses from weathering or volcanic ash, translate into changes in the global carbon budget. In this sense, the smallest organisms sometimes inscribe the most consequential footnotes. The early Earth's greenhouse was partly a biological composition. Methanogens, microbes that produce methane as a metabolic byproduct, are a prime example. In the Archean, before oxygen accumulated, methane could have been abundant enough to thicken the greenhouse, helping keep the surface warm under a faint young sun. Methane is ephemeral on an oxygenated planet. It oxidizes into CO2, water, and in the process, driven by photochemistry, can produce organic hazes that alter insulation. The balance between methane production and oxidation is thus a biological lever on climate. A bloom of methanogenic activity in wetlands or the ocean could nudge global temperatures, the subsequent oxidation or burial of methane could write a chemical footnote that future geochemists might read as a transient excursion. Mass extinctions are the dramatic, editorial acts in which a large swath of biological text is excised and the remaining vocabulary must reorganize. The interplay of life and climate often plays a central role. Volcanically driven greenhouse episodes flood the atmosphere with CO2 and sulfur gases. Oceans warm and stratify. Oxygen dissolves from deep waters and marine ecosystems suffocate. Conversely, the proliferation of photosynthesizers and the widespread burial of organic carbon can draw down greenhouse gases and usher in cooling. When extinction removes dominant groups, it opens niches, blank margins where novel forms can emerge. The Cambrian explosion after earlier, subtler rewritings of environmental conditions. The recovery phases after mass die-offs are periods of rapid proofreading, of punctuation being rethought. Each of these cycles of loss and renewal is both a biological consequence and a climatic catalyst. That duality, organisms shaping climate and climate shaping organisms, operates through mechanisms that are tangible and measurable. Silicate weathering, for instance, is a chemical reaction accelerated by plant roots and microbial activity. As roots pry and secrete organic acids, minerals dissolve more readily. Dissolved ions flow to the ocean and participate in carbonate precipitation, removing CO2 from the atmosphere on multi-million-year timescales. The evolution of roots and soils, therefore, constitutes an engineering project with global reach. Similarly, the oxygenation of the atmosphere was not a passive chemical accumulation, it was a cumulative record of biological, burial organic matter produced by photosynthesis and then sequestered rather than respired. The balance of burial versus remineralization determines redox states. Redox states determine greenhouse gas concentrations and ocean chemistry. Ocean chemistry determines which metabolisms are viable. Feedbacks tighten like screws. Equally important are the ecological engineers organisms that physically restructure habitats. Beavers in a modern landscape are a small-scale analog of broader principles. By damming streams, they create ponds, alter sedimentation, and change methane fluxes. On longer timescales, reef-building corals and stromatolitic mats construct carbonate platforms that redirect currents, trap sediments, and create localized environments conducive to further biological activity. The rise of bioturbating animals, organisms that churn sediment, transform the seafloor from a quiet depositional surface into a biologically reworked layer, where burrowing intensified, oxygen penetrated deeper into sediments, increasing organic matter decomposition and reducing long-term carbon burial. Thus, a morphological innovation. Mobile, burrowing body plans became an editing tool that changed the global carbon cycle and, by extension, climate. The record of these interactions survives, but it survives with caveats. Fossils. Those marginal notes are notoriously selective. Hard parts fossilize more readily than soft tissues. Shells and bones preserve, where rapid burial and anoxic conditions prevent decay. Trace fossils. Burrows, tracks, grazing marks, or behavioral annotations that often give richer context for ecology than isolated bones. But preservation bias is inevitable. Whole ecosystems, even complex forests or intricate reef communities, can be reduced in the rock record to a thin smear of organic carbon, a radar-like band of bone fragments, or a subtle isotopic tilt. The geological library is annotated by opportunistic survival. The fossils left behind are marginalia, not complete copies. Still, some fossils are emphatic. Banded iron formations record large-scale changes in ocean redox. Black shales record episodes of high productivity and anoxia. Coal seams are compressed narratives of vast swamp forests. Geochemical markers. Stable isotope ratios of carbon, oxygen, sulfur function like editorial stamps. They reveal shifts in primary production, temperature, and oxidation states. The advent of an anomalous Toine-CC excursion, for instance, announces a massive input or removal of light carbon. In many instances, what survives is chemical shorthand rather than narrative prose. A fingerprint that suggests a biological actor but rarely reads like a straightforward recipe of who did what. This is where the concept of editing becomes both metaphor and methodology. Evolution acts like a red pencil and an ink pen. Natural selection strikes out maladapted forms. Speciation adds phrases and clauses that expand descriptive power. But these biological edits have cumulative physical effects. The repeated replacement of one functional group by another, say, mat-forming microbes by grazing animals, changes sediment structure and oxygenation, which then changes which molecules are buried and which are returned to the atmosphere. A single innovation, mobility, calcification, lignified tissues, can alter the trajectory of global cycles. Viewed this way, evolutionary novelty is not solely a biological curiosity, it is a planetary instrument. There is a melancholic clarity in recognizing how much gets erased. The Earth's palimpsest is generous in its fragments but stingy in continuity. Entire floras and faunas have left only isotopic size. The taphonomic filters, the conditions that allow material to survive, are narrow. Rapid burial in an anoxic delta or a deep marine basin is a rare accident in geological terms. Uplift, erosion, metamorphism, and subduction are relentless editors that obliterate. Even when a biological signal persists, it is often ambiguous. An enrichment of certain trace elements could be industrial in origin or volcanic. A negative carbon isotope excursion could be methane eventing or the burial of organic matter. The reader of Deep Time often encounters equivocal marginalia. This epistemic modesty carries an ethical undertone. If biospheric activity can alter climate, and climate in turn determines which biological records survive, then the present era's transformations will be recorded not just in local archaeology, but in planetary chemistry. Anthropogenic burning of fossil fuels, large-scale land use changes, the spread of novel organisms across biogeographic barriers, each will leave traces. The Anthropocene, whether labeled formally or not, is an editor's flourish set down in a thin but globally distributed layer. Carbon isotope shifts, new metal distributions, microplastic miscellany. In the distant future, those marks may be the most legible testimony of an industrialized biosphere. Even if architectural ruins and cultural artifacts are gone, there is also a cautionary symmetry. Past intervals when radiation and collapse alternated teach that biological systems can both stabilize and destabilize climate. The proliferation of photosynthetic organisms stabilized atmospheric chemistry in some epochs. In others, the release of greenhouse gases from volcanic cascades or thawing clathrates accelerated warming. Feedbacks are neither inherently corrective nor inherently catastrophic. They are context-dependent. An innovation that appears beneficial at one scale can become destabilizing as it scales. The colonization of land by massive forests led to coal-forming sequestration that lowered CO2 and triggered cooling. That same Sequestration, decades later, became the source of fossil fuels whose combustion is now flipping the system in the opposite direction. The planet's editorial apparatus contains loops whose outcomes are contingent and sometimes perverse. The emotional tone that arises from this duality is complex. There is an abiding wonder at the scale of interplay, that microbial mats could alter atmospheric chemistry, that tiny plankton could precipitate the chalk cliffs of an era, that root hairs could tweak global heat balance. There is also a somber recognition of fragility, that lineages vanish, that their legible traces may be reduced to isotopes and occasional fossilized footprints, that whole ecosystems may be annihilated and leave only faint chemical echoes. Together, these feelings produce a humility in reading Earth's book, a deliberate caution against grand narratives drawn from sparse notes. Methodologically, the imperative is to read across disciplines. Paleontology identifies morphological phrases. Sedimentology interprets depositional tempos and contexts. Geochemistry reads the ink. Climate modeling reconstructs the broader consequences. Only by stitching these perspectives can a coherent reading emerge, one that understands both the local fidelity of buried chapters and the broad strokes of planetary editing. The science is forensic and literary at once, a cautious reconstruction that prizes multiple converging signals over single seductive markers. Ultimately, the lesson is simple and unsettling. Each time life edits by appearing as a new dominant form or by disappearing in a mass die-off, it changes the subsequent legibility of the planet's text. Fossils will remain the marginal notes, the footnotes of events that once unfolded in full prose. Sometimes those marginalia are eloquent enough to allow reconstruction. Sometimes they are so fragmentary that entire civilizations of organisms, if they ever rose to technological complexity, could be reduced to a chemical smudge. The knowledge of this tendency presses a question beyond pure curiosity. What does the current edit look like in the long ledger, and how will future readers parse it? The narrator closes this reflection with a reminder of reciprocity. As the biosphere has authored and reshaped climate, so too will the choices made today be inked into the margins of a book that will outlast its writers. 9 chapters in, handwriting grows more complicated. The next edits will determine whether the following pages are legible, chaotic, or erased. 9. Trish stands as a punctuation mark in that continuing, precarious composition. How many pages were truly lost in the fire? How many paragraphs were crumpled into ash and sent to the winds? The question arrives as a precise, terrible image, an entire library reduced to smoke, and the reader left to pick through blackened fragments and singed margins. It is a useful image because it nails the scale of a problem that otherwise swims in abstractions. The Earth's archive is being both burned and buried, chemically altered, and mechanically ground to dust. The crux of inquiry is not merely cataloguing what remains, but estimating what proportion of the original text, the planet's memories, can still be read, and by what methods. There are 2 ways to approach this: empirically, by examining the record that survives and quantifying preservation biases, and conceptually by defining what counts as memory. Is memory the morphological presence of bones and buildings? Is memory chemical, an isotopic skew preserved in carbonate and clay? Is it behavioral, traces of activity encoded in sedimentary structures? Each definition changes the arithmetic. If a memory is a distinct artifact, an intact building, a scroll, a circuit board, then the probability of survival over millions of years collapses to almost zero, except in exceptionally fortunate contexts. If memory is a chemical or mineral fingerprint, the telltale 13C excursion from a burst of fossil fuel combustion, plutonium isotope in a layer of clay, then the fraction that survives is markedly larger, because such signals can be widely disseminated and locked into resistant minerals. Start with the fossil record as an instructive model. Paleontologists have long accepted that morphology is a poor, biased sample of past life. Hard parts fossilize, soft tissues do not, unless rapid burial and anoxia conspire to protect them. Whole ecosystems can vanish, leaving only micrograms of molecular residue, or sometimes merely an isotopic wobble. For many groups, the skeletal record may represent a tiny sliver. Often cited figures range from a few tenths of a percent to single-digit percentages of species that ever lived. The record of entire communities, behaviors, and cultural complexity is yet more precarious. From that vantage, the planet's memory of biological diversity is grossly incomplete, an anthology of fragments rather than a comprehensive corpus. But the planetary archive is more than morphology. It also records flux, chemistry, tectonics, climate, These records are sometimes global and synchronous. They can be mapped across basins and therefore are more robust indicators of systemic change, a global carbon isotope excursion, a sulfate spike, a layer of iridium. These are the loud lines in the book. They may not tell the whole narrative of who walked the stage, but they signal the acts that rearrange the scenery. Thus, when one asks what percentage of planetary memory can be read, an answer must distinguish between the survival rate of discrete objects and the survivability of systemic signatures. Consider the likely fates of different classes of signal over mere timescales, textured artifacts and architecture, buildings, art, and other structured cultural objects require both material durability and stable burial to survive in any recognizably intact form. Most architectural materials are vulnerable. Metals corrode, concrete fractures under stress and fluid circulation, wood rots or is consumed. Only particular materials, certain ceramics, vitrified glass, some noble metal alloys, resist chemical breakdown. Even these must avoid uplift, erosion, and subduction. Consequently, the probability that a randomly sited complex structure will survive intact for tens of millions of years is vanishingly small. The small subset that can survive will do so only in rapid burial environments or in tectonically stable basins deltaic deposits, and noxic lakes or deep-sea fangs that are later protected by burial and lack of subsequent uplift. Small durable objects and mineral traces, ceramic fragments, certain high-fired glass, and some synthetic polymers have greater longevity than organic matter but are still susceptible to diagenesis and mechanical breakdown. Microbeads, microplastics, and tiny glass spherules can be dispersed widely and buried in fine-grained sediments as particulate markers. They may persist longer than large intact artifacts because of their ubiquity and capacity to be entrained into depositional sinks. Their presence in a given horizon can be detected in thin sections and geochemical assays long after artifacts themselves have been pulverized. Geochemical and isotopic anomalies, shifts in isotope ratios, unusual trace element concentrations, spikes in radionuclide abundances, these are among the most resilient signatures. Isotopes become locked into minerals, carbonates, and organic matter. Radionuclides are measured precisely and can be distinguished from natural backgrounds. A relatively small anthropogenic perturbation to global carbon cycling, if large enough and abrupt, can imprint a clear CC. Excursion preserved the marine sediments worldwide. Similarly, fallout radionuclides produced by nuclear fission have a distinctive, long-lived fingerprint. Such signals are relatively robust across the stratigraphic record, provided that the strata themselves survive burial and are not metamorphosed beyond recognition. Structural and sedimentary alterations, large-scale changes to sedimentation, dams, land use shifts that change erosion rates, urbanization that alters sediment flux, leave geomorphic signatures, modified stratigraphic thicknesses, increased terrigenous input. Anomalous metal concentration in riverine deposits. These are not readable as sentences, but as systemic deviations, edits in the rhythm of deposition. Because they operate at landscape scale, they have a higher chance of being recorded in the stratigraphic column, albeit in a distributed and often ambiguous way. When these classes are tallied together, a composite picture emerges. The survival of discrete artifacts, legible pages with sentences intact, is rare. The survival of systemic signatures, ink stains, smudges, and sometimes whole paragraphs of altered geochemistry is far more probable. So what percent? The honest answer is, it depends on the question you ask and on the time scale. If the question is, what fraction of material culture buildings, books, intact artifacts will remain legible after 10 million years? The percentage approaches zero for most of the planet. Only a minute portion, objects fortunate to be buried in anoxic, rapidly accumulating sinks and composed of extraordinarily durable materials, would be recoverable. If the question is, what fraction of global biogeochemical change is likely to be recorded, the range widens. Prominent, rapid perturbations, those that alter atmospheric carbon, oxygenation, or deposit globally distributed aerosols, can leave a signal in a large fraction sedimentary basins. In other words, the narrative of systemic change is more resilient than the narrative of detail. Any attempt at a blunt numerical estimate must therefore specify the denominator. For morphological species level richness, the fossilization probability for marine invertebrates is often suggested to be on the order of 0.015%, depending on clade and depositional environment. Cultural artifacts are likely orders of magnitude lower because the combination of material vulnerability and geological recycling is severe. Conversely, the fraction of errors that leave notable geochemical signatures, major volcanic episodes, bolide impacts, and abrupt climate excursions can be higher. These events are sometimes written into sediments worldwide and can be detected in many basins. But statistics conceal a crucial spatial heterogeneity. Preservation is place-dependent. Sedimentary basins that accumulate rapidly and remain stable, for example, large deltas, certain intracratonic basins, and restricted anoxic shelves act as archival pockets where even fragile things have a chance to be entombed and catalogued. Conversely, high-energy continental margins, mountain belts, and oceanic crust destined for subduction are poor libraries. The geography of survival is therefore patchy. A civilization perched above an epic delta has a far better chance of leaving a geological whisper than one perched on a long-lived origin that will be later uplifted and scraped clean. There is also a temporal bias. Rapid events that produce thick tephra layers or large, abrupt chemical excursions have a better chance of being correlated globally and hence recognized. Slow, incremental changes, cultures that rise and fall without large-scale geochemical perturbation, may leave only local, easily destroyed marks. Catastrophes can paradoxically be both erasers and recorders. They destroy local detail but imprint a thin, widespread horizon that remains legible across basins. Measurement capabilities matter. One of the reasons modern scientists can reconstruct ancient events that happened hundreds of millions of years ago is the development of high-resolution geochemical tools, mass spectrometry, microprobe imaging, and high-precision radiometric dating. These technologies transform faint smudges into legible sentences, but the record itself must contain those smudges. No instrument can resurrect patterns where none were preserved. Beyond raw detectability lies epistemic ambiguity. Many chemical signals are multi-causal. A shift in carbon isotopes could reflect changes in organic burial, methane release, volcanic emissions, or biological productivity. A metal spike could be industrial or volcanic. Distinguishing an anthropogenic origin from a natural one in ancient rocks requires a constellation of lines of evidence. Co-located isotopic anomalies, unusual concentrations of rare anthropogenic elements in forms inconsistent with natural, geochemical cycling, and a depositional context susceptible to rapid variation. The stronger the multiplex of independent signals, the higher the confidence. But even then, uncertainty remains. That uncertainty has both scientific and emotional valence. It inspires humility. The reader who recognizes how much is irretrievably lost must also reckon with how easily a coherent narrative can be fabricated from coincidental correlations. It elicits a kind of melancholy, the thought that whole eras, whole ecologies, or even the handiwork of complex minds might be reduced to a thin smear of chemistry, is a small grief. Yet there is also curiosity and a stubborn optimism. Even in shards, the planet's pages speak, and ensemble methods integrating sedimentology, geochemistry, paleobiology, and stratigraphy can recover surprising amounts of history. From a practical standpoint, the exercise of estimating recovered fraction advises strategy. To maximize what will be legible to distant readers, interventions would aim at the places and media most likely to survive: deep, rapidly accumulating basins, anoxic depositional environments, mineral matrices that sequester isotopes and trace elements, and chemically exceptional markers that cannot be produced by natural processes without a strong, unusual forcing. In the absence of deliberate archival strategy, the planet will do the selecting. The sedimentary conveyor will choose which fragments are retained and which are surrendered to the mantle or to the winds. The lesson is not merely scientific, it is ethical. The fragility of planetary memory reframes stewardship. If the survivability of testimony is so contingent on place, on process, on chance, then humanity's choices about how to alter landscapes in chemistry take on a new moral weight. To write an indelible line into the book requires not only bold action but careful attention to the conditions of preservation. Conversely, reckless, diffuse alteration risks erasing not only past archives but also the future's ability to read what has been done. In the end, the percentage of planetary memory that can be read is less a fixed number than a conditional probability. For whole artifacts and architecture, that percentage is vanishingly small. For geochemical fingerprints of major, abrupt perturbations, it may be appreciable, perhaps detectable across tens of % of sedimentary basins. for the full narrative richness, the nuanced, textured story of ecosystems, cultures, and behaviors. The surviving fraction is tiny, an anthology of fragments rather than a comprehensive library. That is the quiet, double-edged truth of the palimpsest. Much of what matters is ephemeral. Some of what endures is surprisingly informative. Paleoclimate and geochemistry can read systemic chapters, taphonomy and fortuity, determine whether the margins retain the fine print. The earth will continue to smudge and to preserve an unequal measure, and readers of deep time will continue to ply patient, interdisciplinary methods to coax sentences from the ash. 10. Lie. What does it mean to stand in the present and call it an epoch when every ridge and seam, every buried peat bed and oil trap has been reclassified as material, a stockpile of sentences to be cut out and repurposed? The question folds back on itself. Humanity has become both reader and bookbinder, scholar and arsonist. Mountains become quarries, coal seams, once slow compactions of ancient forests and swamps, are now fuel for furnaces that write new chemical notes into the atmosphere. Oil and gas, the slow-inked residues of marine burial, are tapped and burned as if they were disposable page fragments. Sediments, the careful layers that once recorded storms, seasons, and sea level changes, are scraped, dredged, dammed, and shipped. The land becomes an archive from which chapters are extracted to power a different kind of narrative, one of industry, heat, and immediate utility. This is a peculiar form of reading. In the classical image of the archive, the reader turns pages with reverence, preserving margins and noting provenance. The modern human reader of Earth's history has another habit. While sampling the library, they also tear out pages to feed the fire. Core drilling and coring are acts of both curiosity and consumption. Each scientific borehole yields information. A tiny spool of stratigraphy opened and translated, and yet it is also a wound, an incision whose extraction rearranges the very context one seeks to understand. Mining and drilling operate at a different scale, but the logic is the same: to make use of the planet's stored capital, to convert long-accumulated geological sentences into heat and motion, to trade a chapter of deep time for a moment of immediate energy. The irony is not merely rhetorical. Many of the very processes that increase human knowledge about deep time also accelerate its erosion. Open-pit mines expose stratigraphic relationships once buried beneath meters of soil and rock, revealing pages that would otherwise be hidden. But exposure invites weathering. Exposed bedding planes are more easily stripped, reworked by rain and wind, and their contextual coherence is lost. River diversion, dam construction, and channelization change sediment delivery systems. Where a river once carried fine, annually layered sediments into a quiet basin, a high-fidelity recorder of seasons, it may now be trapped behind a concrete wall, the downstream archive starved of the very material that would hold the human signal. Where sediments once leisurely accumulated in deltas and estuaries, humans have accelerated burial in places and prevented it in others, choosing which local stories get thickened into lasting strata and which are denied the quiet anoxic seam that would preserve them. There is a strong, almost paradoxical truth in this. Extraction both creates and destroys preservation opportunities. Rapid burial in a delta or an anoxic basin enhances preservation. A floodplain turned into a reservoir may, for a while, protect organic matter and human detritus beneath lacustrine clays. Conversely, urban sprawl, plowing, and deforestation increase erosion, erasing topsoil and the surface context of artifacts. In one landscape, a discarded object might be quickly entombed in fine mud and, under the right geochemical conditions, survive for millions of years as part of a stratigraphic page. In another, it will be exposed, degraded, crushed, and redistributed as dust. The planet's archivists are indifferent. They respond to fluxes of energy, sediment, and chemistry, not to any ethic of preservation. The materials humans exploit carry their own stories and their own tendencies toward survival. Coal seams, for instance, record a particular kind of biological and environmental narrative. Vast swamp forests grew, died, and were buried in waterlogged, anoxic conditions which limited decomposition and allowed plant tissues to accumulate. Those seams are themselves chapters of the biosphere, pages of living landscapes written in lithified carbon. The act of mining and burning coal is a strange reversal. What once sequestered atmospheric carbon for geologic timescales is now liberated and re-entered into the atmosphere in a few short centuries, changing the chemistry of the global book. In turn, that release inks new, widespread chemical strokes into sediments, isotopic excursions, acidified oceans, and altered sedimentation patterns that may persist far longer than the ephemeral factories that produced them. Oil and gas amplify the same paradox. Hydrocarbon reservoirs are the long-encoded residue of organic productivity, burial, and thermal transformation. They are, materially, a compressed narrative of ancient seas and burial regimes. Extracting them does not merely provide energy, it transposes a long-closed chapter into present dynamics. The combustion products disperse globally, a light carbon signal carried into the atmosphere and oceans, a chemical stain that will be incorporated into future carbonate layers, into organic, rich shales, into the very fossils that future readers will interrogate. The Anthropocene, if it leaves a distinct mark, will be partially written in the isotopic composition of carbonates and organic matter, a thin but globally coherent line that whispers of fossil carbon suddenly return to circulation. Other anthropogenic materials write differently. Plastics, for example, are not merely refuse, they are particulate ink. Microscopic beads, fibers, and fragments pervade soils, sediments, and the deep sea. Unlike many organic compounds, certain plastics resist chemical breakdown at Earth-to-surface conditions and can accumulate as persistent particulate matter in sheltered depositional environments, seabed fans, abyssal plains, and perdelta clays. Microplastics and their chemical degradation products can be trapped, mixed with pollen and ash, and incorporated into the stratigraphic page. To a distant geologist, a horizon rich in microplastics could appear as a novel, inorganic sedimentary component. Its chemical signatures, plastics, leachates, synthetic pigments, or persistent additives could act as unambiguous technofossils. Glass and certain ceramics also endure. High-fired pottery shards, vitrified sands, and specific alloys resist alteration longer than organic matter, making localized archaeological legibility more plausible in certain depositional niches. Yet persistence is never guaranteed. The chemistry of burial, subsequent diagenesis, and the possibility of tectonic upheaval conspire to erase. Plastics embedded in sediments may be subject to microbial degradation in anoxic environments, to hydrolysis under heat, or to incorporation into orthogenic minerals over geologic time. Metals corrode, alloys diffuse into mineral lattices, and concrete becomes a rock that, under pressure and heat, recrystallizes into something that resembles natural lithology. Even radionuclide markers, the fallout products from nuclear fission, while short-lived on some scales, leave daughter isotopes and chemical anomalies that can be detected, but those too can be diluted, mobilized, or locked into mineral phases that later recrystallize. The longevity of any technogenic signature depends on context, sedimentation rate, redox state, burial depth, and tectonic fate. That context is itself being remade by human activity. Large-scale land use changes alter erosion and deposition patterns. Deforestation increases sediment flux to rivers, which in turn enhances deltaic burial in some regions and coastal erosion in others. Dams interrupt the conveyor belt of sediment, trapping it behind reservoirs and starving downstream basins that might otherwise sequester anthropogenic detritus. Channelization straightens rivers, reducing the formation of meanders, oxbow lakes, and floodplain laminations, all settings that are more likely to preserve layered records. Coastal engineering projects, seawalls, levees, and reclaimed land fold modern materials into the substrate, burying human-made strata beneath concrete and fill. In this sense, humanity is editing the grammar of preservation, choosing which depositional contexts will be active and which will be sterilized. There is also the slow chemical rewriting of soils and sediments that deserves attention. Industrial fixation of nitrogen through the Haber-Bosch process has massively increased reactive nitrogen in terrestrial and aquatic systems. That surplus leaves a detectable signal: altered nitrogen isotope ratios in soils and sedimentary organic matter. Fertilizers, sewage, and altered agricultural practices change the delivery of phosphorus and trace metals to the ocean, affecting planktonic communities and thereby modifying the nature of organic burial. The biogeochemical cycles that undergird the geological record are now partly authored by human practice. The chemistry of the archive is being shifted, even as its physical pages are mined. Emotion threads through these observations. There is a compact of conflicting feelings, a pragmatic satisfaction in the ability to mobilize resources, a small and private pride in the ingenuity that transforms buried carbon into light and motion, and an abiding grief at the knowledge that such transformations are etching a thin, unmistakable band into the face of the planet. The metaphor of reading while burning is not merely rhetorical, it captures an ethical tension. To learn about Earth's history, humans must sometimes remove material, take a core, collect a sample. But the scale and intent of contemporary extraction exceed scholarly curiosity. They are systemic, disruptive, and aimed at consumption. The planet's book is being both read and cannibalized. This tension yields a practical paradox. Some acts that damage the preservation potential of the planet also, ironically, reveal hidden pages. An open pit stripped to bedrock exposes fossils and stratigraphic relationships previously inaccessible, enabling new reconstructions of past ecosystems. Urban development, which often obliterates surface strata, can also unearth artifacts and bones during construction. Yet the discoveries these disturbances enable do not compensate for the wholesale loss of context and the conversion of layered, readable signals into dispersive detritus. A recovered fossil from a mined face is an exquisite but compromised testimony, a single sentence torn free of its paragraph. There is also another, subtler kind of destruction, the conversion of geological processes into industrial analogues. Where rivers once oscillated with seasonal floods, their flows are now controlled by hydroelectric dams whose reservoirs substitute for natural floodplains. Where wetlands once sequestered carbon and preserved organic layers, they are drained for agriculture or urban development. The planet's physiological systems, its flood regimes, sediment transport, and soil formation processes are being rerouted. These changes alter where sedimentation occurs, where anoxic conditions can persist, and where human detritus may be finally entombed. The Anthropocene, in this reading, is not a single layer, but a reconfiguration of the processes that produce layers. Toward the close of this present chapter 1, must ask a deliberate, patient question: what is the fidelity of the record being created? Will future readers find a neat stripe, a single, globally synchronous marker that announces a sudden perturbation, or will they confront a messy collage, a mosaic of local anomalies and dispersed particulate signatures? The answer, in truth, will be both. Some global indicators are already readable: a pronounced isotopic excursion in carbon, a spread of radionuclide anomalies in the mid-20th century, the first appearances of microplastics in marine sediments. Others will be highly regional, thick anthropogenic sediment wedges in rapidly subsiding deltas, atypical heavy metal concentrations in mining impacted basins, and urban lithofacies composed of concrete rubble, slag, and compacted refuse. The geological future will, therefore, carry both bold headlines and faint marginalia, and yet the story does not end with resignation. There are choices embedded in this moment, which depositional contexts do humans preserve. Which chemical markers are deliberately created to signal purpose? If a society wanted to leave a legible, deliberate archive, an instruction set for distant future readers, it would seek chemically durable media, rapid burial, and avoidance of subsequent heat and tectonic reworking. Absent deliberate effort, the planet's mechanical editors will choose sedimentary basins, anoxic shelves, and rapidly aggrading deltas will be the most likely repositories of our inadvertent testimony. The final note of this chapter is neither triumphalism nor elegy. It is an observation of consequence. The present system, the mountains excavated for ore, the coal seams burned for energy, the reservoirs built and the channels straightened, is simultaneously a set of alterations to Earth's functioning in a program of selective preservation. Humanity reads the planet's book intensely and, in so doing, rewrites the margins. The library is not merely consulted and catalogued, it is harvested and often consumed. To stand at this threshold is to sense both agency and humility, the ability to change planetary processes and the limited control over which of these changes will persist in a lithified future. There is, appended to that humility, a quiet anticipation. What will the next chapter, the speculative turn, look like? If part of the present is the conversion of buried biotic capital into atmospheric and sedimentary signals, then the speculative question is whether future readers will interpret those signals as natural perturbations or as the fingerprints of an industrious intelligence. The lines are faint, but they exist: isotopic excursions, an array of technofossils, an alteration of sedimentary regimes. What follows is not a tale of certainty, but an inquiry. The archive is being altered even as it is read. The next section will ask how to distinguish between natural variation and deliberate imprint, between the accidental stains of industry and the possibility of intentional, durable signaling. In the quiet after extracting a core or a coal block, the planet offers both a lesson and a warning. Pages may be legible, but the act of reading has consequences. The next chapter will explore the imaginative directions those consequences might take. What if, for an instant of imagination, the Earth's book had never been mutilated? What if every folio, from the molten first strokes to the newest ink-smeared margins, had remained bound and legible, no pages lost to subduction, no lines blurred by heat, no chapters shredded by erosion? The question is not merely a whimsical longing for completeness. It is a counterfactual experiment that sharpens the mind. What would it mean to read a continuous, high-resolution manuscript of planetary history? What knowledge would arrive as certainty rather than inference? Which surprises, hidden chapters, unforeseen patterns, silent actors might be revealed in a single, unbroken archive? The immediate scientific consequence is simple and profound: the removal of many of the ambiguities that now haunt interpretation. At present, scientists are detectives of absence. They pull threads, an isotope excursion here, a thin ash bed there, a fossil assemblage out of time, and weave narratives that must always acknowledge gaps. An intact book would be a different task. It would transform the work of piecing into the work of reading. The chronology of cause and effect would be visible in far greater fidelity. The tempos of events that now appear as thin underlinings, a glacial advance, a volcanic pulse, a pulse of biotic radiation, would read as full sentences with prefaces and afterwords. Scientists could follow the slow accumulation of heat in the mantle and then watch, page by page, the chemical response in oceans and the resulting biological turnovers. Abrupt isotopic swings would no longer be enigmatic blips. They would be mapped to preceding processes with place and time precision. Such completeness would reshape not only the scale of certainty, but the kinds of questions asked. Rather than debating whether a particular science fantasy excursion resulted from volcanism, methane release, or a massive organic burial, the readers of a pristine stratigraphy could trace the antecedent steps, the pattern of rainfall, the pulses of erosion delivering nutrients, the local blooms of plankton, the submarine vents disgorging methane, the interplay of tectonics and climate, how the uplift of a mountain range slowly, over millions of years, nudged atmospheric composition, and then, with delay, reorganized ocean chemistry would be visible without recourse to patchwork inference. The atmospheric composition through deep time would be a flowing graph in the margin, not a series of disconnected notches. That resolution carries a second gift, the possibility of discovering chapters no one expected. If entire continental shelves and seafloors had been preserved, they would be full of lives and events that plate tectonics usually hides. The ocean floor, older than 200 million years, is largely absent today. Yet much evolution and many ecological experiments undoubtedly played out upon it. An intact record might reveal long epochs of ecological novelty, entire marine provinces dominated by now-forgotten body plans, blooms of microbial ecologies adapted to chemical regimes that no longer exist, repeated experiments in ecosystem engineering that left only subtle chemical markers today. In short, the palette of past biospheres could be far broader than the fragments currently allow us to imagine. The question that stirs more public imagination, what would an intact book say about civilization-scale phenomena, cannot be evaded, but it must be handled with care. If a technologically complex society had arisen long before Homo sapiens and then vanished, what traces would it leave? In a perfect archive, the answer becomes clearer: large-scale, durable chemical and isotopic anomalies, layers rich in synthetic materials, abrupt stratigraphic horizons containing manufactured isotopes or alloys in forms inconsistent with natural processes. A continuous, unaltered sequence would show not merely an isolated anomaly, but a context preceding economic and environmental trends, the rate of change, and the aftermath, where the present record forces scientists to ask whether an isotope spike was industrial or volcanic. The intact record would allow them to assess patterns across space and time. Are there repeated, regionally coherent anomalies tied to altered land use, to concentrated mining and smelting signatures, to persistent accumulations of inorganic polymers, or to nuclear fission products in the expected decay chains? The power of such a record would be its capacity to discriminate cause from coincidence. Yet even an intact book does not guarantee unambiguous answers. The planet's language is complex and sometimes convergent. Natural processes can mimic industrial ones. Volcanism and biologically mediated fractionation can produce similar isotopic patterns under certain conditions. The reader's task would still require a sophisticated literacy and ability to read multiple, intersecting lines of evidence, but the margin of interpretive error would shrink dramatically. The uncertainty would move from whether an event happened to the nuance of how it unfolded. beyond purely scientific gains. An intact record would transform human self-understanding. The present perspective, an infinitesimal comma in a long sentence, carries a potent humility. Were the book intact and legible, this humility would be accompanied by a new historical awareness. Humanity could read, with much greater clarity, the planet's episodes of resilience and collapse, the rhythms by which ecosystems reorganized after perturbations, and the durations required for recovery. It would be possible to identify recurring motifs, intervals when ecosystems underwent repeated reorganizations, periods when technological intensities correlate with ecological stress and rapid turnover, and examples of long timescale stability that are surprisingly fragile in practice. Those patterns would not simply satisfy curiosity, they would be a mirror held up across ages, revealing the trajectories that can lead to stability and those that predispose systems to catastrophic reconfiguration. That mirror holds both consolation and disquiet. On the consoling side, a full book might show that life's capacity for reinvention is deep cycles of extinction, followed by radiations that reassemble complexity in novel ways. The record could offer evidence of long, patient recoveries where systems reorganize into new equilibriums. On the worrying side, a comprehensive archive could also reveal recurring modes of failure, thresholds crossed with similar consequences, feedbacks that amplify rather than dampen change, and the fragility of complex systems when subjected to certain stresses. Seeing patterns repeated over hundreds of millions of years reframes philosophical questions about inevitability and contingency. Human agency becomes measured not merely by uniqueness, but by the degree to which present actions resonate with reliably destructive trajectories or with routes to sustainable reconfiguration. An intact book would also be a different kind of moral document. Today's fragmented archive fosters an ethic of humility, the recognition that vast swaths of history are irretrievable and that interpretations must be tentative. A complete archive would impose a new ethic of accountability, knowing the precise outcomes of past actions, how certain extraction practices led to long-term contamination, how specific land use patterns accelerated erosion, or how the introduction of certain species cascaded into mass extinction would impose clearer lessons. The past would cease to be a series of remote puzzles and become prescriptive evidence, rich guidance on which pathways yielded resilience and which precipitated collapse. Such clarity could inform policy, conservation, and stewardship in ways the present partial record tends not to. That is not, however, a guarantee of wisdom. Knowledge does not translate automatically into action. The book could be opened, read, and set aside. Understanding the mechanics of collapse does not ensure the political will to avoid them. The ethical exigency embedded in an intact record would be only as meaningful as the choices made in response. Imaginative utility aside, the technical implications are worth pausing over. An unbroken stratigraphic record would revolutionize chronology. Radiometric age models that now depend on scattered tephra layers and regional correlation schemes would be continuous. Paleomagnetic reversals, orbital cycles recorded in sedimentary rhythms, and isotopic cycles would interlock in a precision rarely achievable today. The history of rates, how rapidly CO2 can accumulate given certain boundary conditions, how fast ocean anoxia can develop, how quickly ecosystems can lose functional diversity would be empirically resolvable rather than model-dependent. Those rate constraints are crucial. They govern the window between warning and catastrophe. A pristine book would shrink that window into measurable, actionable timeframes. There is, too, an epistemic humility encoded in the imagining of an intact record. Even with perfect data, interpretation is not a mechanical process. Language is laden with metaphor. Even the best preserved lines can be read differently by readers with different priors. A continuous archive reduces ambiguity but cannot eliminate the human tendencies to favor compelling narratives, to weigh certain lines of evidence more heavily, or to project continuity where there may be contingency. The book would be a powerful instrument for clarity. It would not be an oracle. Finally, the counterfactual helps to illuminate the smallness and the weight of the present. If the book had been preserved intact, the passage of humanity would be a footnote among many, but an unusually bright one in chemical ink. The anthropogenic isotopic signatures, the record of plastics and radionuclides, the altered landscapes. These would be unmistakable typographical features in a continuous record. The choice, then, is not whether humans will leave a mark, but what that mark will say. The palimpsest of the earth suggests two possibilities: an inscription that aids future readers in understanding and navigating planetary systems, or a smudge that obscures previous stories and leaves scarcely legible aftermaths. The counterfactual, in its end, becomes prescriptive. If completeness of record would have clarified so much, then preserving what can still be preserved has a new urgency. That includes deliberate archival strategies, depositing durable, intentionally designed markers in stable, rapidly accumulating basins, creating chemical beacons that are unambiguously synthetic, and curating repositories' time. Capsules, not as nostalgic gestures, but as serious contributions to planetary memory. It also includes the less glamorous but essential work of stewardship, slowing erosive practices, protecting wetlands and deltas that can entomb the present for eons, and limiting activities that inject ambiguous, globally diffuse signals into the environment. There is a quiet finality in this thought experiment. The Earth will never revert to a pristine manuscript. Subduction will continue, metamorphism will persist, and erosion will keep its patient bookkeeping. The palimpsest is the permanent condition, layers written, erased, and rewritten in a rhythm older than any human project. Yet the counterfactual serves a purpose beyond idle speculation. It sharpens the imagination, clarifies priorities, and reorients responsibility. To imagine a complete book is to perceive more vividly the holes in the one that exists, and to see in those holes not only loss but the terrain where action matters. In the last pages of this imagined volume, the story narrows toward a moral question that is at once simple and vast. What will humanity write next, and how will future readers interpret it? The answer depends on choices made in the near term about energy, about land, about what is valued and what is exploited. The act of reading the Earth's current fragmentary book has been, in a sense, a rehearsal for writing responsibly in a future that will one day be a fragment to others. The intimate lesson of the counterfactual is this: completeness would bring clarity, and clarity would bring counsel. Lacking completeness, humans must act as careful editors of what remains, mindful that every excavation, every omission, and every burial is an edit in a book that will outlast its authors. The Earth's manuscript will keep being written, page by page, in a hand both indifferent and responsive. The honest end of this thought experiment is not a verdict, but an invitation to read with humility, to preserve where possible, and to write the next lines with a consciousness that what is penned today will be read and judged in a long and patient future. In that judgment, perhaps the most human legacy will be less the monuments of stone or the transient sculptures of culture than the deliberateness with which a species chose to be legible, generous, and careful within the vast library it inherits. The book will remain a palimpsest. The last choice is whether humanity will add another layer of erasure or a durable, intelligible note for those who turn the pages yet to come. Which posture will best serve a species standing in a vast, fragile library? That single question reframes the argument that has threaded through every previous chapter. Earth is at once repository and palimpsest, the archive and its own censor. If the planet strata are pages, then the moral and practical task is not merely to decipher what remains, but to decide how to act so that future readers, whose eyes will be trained in geochemistry and patience, can still find anything to read. The conclusion that follows is not a manifesto of certainty, but a set of philosophical recommendations rooted in the lesson of deep time. Read with humility, record carefully, and leave room for those who come after. Read with humility. Humility is not an aesthetic affectation. It is a methodological posture for anyone who works with the long record. The Book of Earth is the most patient text imaginable, and patience requires a different set of virtues than those that govern short histories. Where modern institutions prize speed, clarity, and resolution, the archive of deep time rewards restraint, multidisciplinary corroboration, and an admission of ignorance. To read humbly is to accept three interrelated facts. The record is partial, processes are entangled, and human cognition is biased toward tidy narratives. First, the record's partiality should be treated not as a frustrating obstacle to be overcome with more certainty, but as a feature that shapes questions and methods. Fragmentary pages are not failures of science. They are the terms in which all plausible reconstructions must be phrased. Humble readers therefore adopt a probative stance, seeking multiple independent lines of evidence, privileging convergent signals, and refusing to proclaim grand conclusions from single anomalies. This humility has a practical consequence. It cultivates research programs that favor replication, that place equal weight on negative evidence, and that design inquiries to distinguish between alternative causes rather than to confirm the most attractive one. Second, humility recognizes entanglement. Geological and biological processes cross-influence on timescales that elude direct observation. Humble reading is interdisciplinary reading. Geochemistry must converse with paleobiology, sedimentology with climate modeling, archaeology with systems analysis. The narrator who reads deep time insists that a single specialty cannot be the arbiter of truth about the past. The methods of reading must be plural, their assumptions explicit, and their uncertainties quantified. Third, humility addresses the human proclivity for narrative closure. The mind prefers clean stories, heroes, causes, and consequences, yet the planet's book often offers only motifs, iterated episodes of pattern and contingency. To read with humility is to resist the seduction of neatness and to respect the provisionality of inference. It is to accept that some questions will remain open-ended for centuries and that the value of patient accumulation of evidence outweighs the appeal of rhetorical certainty. Record carefully. If humility governs how to read, careful recording governs what to leave. Recording is at once a scientific practice and an ethical commitment, an act of generosity toward future intelligences. It can be understood on several levels: the preservation of scientific data, the creation of durable physical markers, and the stewardship of environments that act as natural archives. Preserve the data ecosystem. The modern record is as much digital as it is physical. Datasets, code, high-resolution images, and context metadata are the scaffolding future readers will use to interpret layers. But digital media are fragile bit rot. Format obsolescence and centralized failure pose risks. The philosophical recommendation is therefore redundancy of encoding and distribution. Records should be stored in multiple formats, analog and digital, on different substrates, and across geographically dispersed repositories chosen for geological stability. The metadata schema must be robust, minimally dependent on contingent software ecosystems, and must include self-descriptive headers, a Rosetta for future decoders. Equally important is the cultural disposition to maintain these repositories as enduring public goods, funding models. Legal protections and institutional commitments must span generations rather than election cycles. Design durable markers. If an intentional signal is to be left for far future readers, it should be conceived with geological processes in mind. Durable materials, certain ceramics, high-fired glass, noble alloys, and mineral matrices outperform organic substrates. Markers should be encoded redundantly, multiple physical copies, dispersed across several stable depositional contexts, and should include interpretive keys. Simpler is better. Durable geometries, patterned inscriptions, and chemical signatures that will survive diagenesis are more legible than complex electronic media that rely on ephemeral power. At the same time, deliberate markers should be designed to minimize the risk of erasure by standard processes. Deep burial in stable basins, inclusion in orthogenic mineral precipitates, or entombment in lithified sediments increase longevity. In practice, this suggests collaboration between materials scientists, geologists, and archivists to create objects that are both legible across time and resistant to ordinary geological editing. Protect natural archives. Perhaps the most consequential recording strategy is to protect the places where the planet already archives its own past. Peatlands, anoxic coastal basins, restricted shelves, and rapidly prograding deltas are high-fidelity recorders. They accumulate matter quickly under conditions that limit decay and reworking. Conserving these environments is a double win. They sequester carbon, helping mitigate climate change, and they preserve the material testimony of the present. The philosophical stance here is conservative in the literal sense, favor preservation over short-term exploitation where the two conflict. Policies that curtail destructive extraction in these archival settings, that restore wetlands and prevent the draining of peat, and that acknowledge the global significance of these depositories are acts of archival ethics. Leave books for the future. To leave books for posterity is to practice restraint, design thinking, and political imagination. It means recognizing that not every available resource must be consumed now, and that some material legacy should be curated, rather than repurposed. There are three complementary strategies: intentional legibility, spatial prudence, and cultural humility. Intentional legibility. A deliberate archive can be more than a time capsule. It can be an instruction set. Markers intended for deep time readout should aim to be unambiguously synthetic in both form and chemistry, avoiding mimicry with natural signals. This does not imply creating nuclear diagnostics or irreversible contamination. It instead means thoughtful use of materials and isotopic tagging that are unlikely to arise naturally. Such markers should be distributed across multiple stable settings and accompanied by redundant, self-explanatory keys that transcend any single language or symbolic system. The ethical principle is modesty, to provide information that aids future interpretation without imposing wasteful or hazardous materials on later ecologies. Spatial prudence. Geological fate is petulant. A city built tomorrow on a rapidly subsiding delta or within a zone destined for future subduction is less likely to contribute to planetary memory than a small, carefully selected archive sealed in a stable basin. Thus, there is an argument, ethical and practical, for concentrating some archival effort in regions with low tectonic mobility and favorable burial regimes. This is not a technocratic prescription for cultural relocation, but a deliberative choice about where to place intentional repositories and how to protect natural archives. It recognizes the asymmetry of preservation and uses that knowledge to maximize the chance that certain things, data sets, interpretive manuals, durable markers will survive. Cultural humility. Leaving books for the future is not a unilateral act. It is an obligation that engages diverse cultures, democracies, and the global commons. Decisions about what to archive, how to encode it, and where to place it should involve broad participation and respect for differing values. The ethical posture is to avoid colonial or hegemonic assumptions about what constitutes worth preserving. In practical terms, this suggests international frameworks for deep-time stewardship treaties, collaborative institutions, and funding mechanisms that distribute responsibility and guard against the monopolization of planetary memory, practical prudence, and moral imagination. These philosophical recommendations are not mere abstractions. They imply tangible shifts in policy, science, and culture. First, science must prioritize context. Fieldwork and sampling protocols should foreground stratigraphic integrity and minimize destructive practices, where unavoidable extraction should be guided by a principle of archival triage, retain samples, duplicate records, and deposit copies in multiple repositories. Second, governance must incorporate geological literacy. Planning agencies should consult geologists, paleoclimatologists, and archivists when approving projects that alter depositional environments. Third, education must cultivate long time scales. Public pedagogy that broadens temporal imagination, teaching children to think in millennia rather than mere decades, creates the cultural substrate for intergenerational stewardship. There is also a deeper moral appeal in these recommendations. To treat Earth as a library is to accept a shared fiduciary duty. The present generation holds a temporary custodianship over a text that will outlast individual lifetimes, institutions, and perhaps species. That custody is not passive. The act of reading has always changed the book, drilling, sampling, and querying leaf marks, so do mining and combustion. The ethical challenge is to ensure that the marks are thoughtful, restrained, and reversible where possible. A stewardship ethic reframes conservation as an act of literary care, preserving margins, cataloging with rigor, and resisting the impulse to score the pages with callous immediacy. A final caution: the aim is not to freeze humanity or reify the past as sacrosanct. The planet is dynamic, and human needs are legitimate. The philosophical recommendations acknowledge a balance. They insist neither on asceticism nor on unbridled consumption. They prescribe a posture in which development is tempered by an obligation to maintain the legibility of the planetary record. Technological progress and responsibility are not opposites. They are compatible when guided by long-term thinking. Closing reflection. In the archive metaphor, the reader pauses not merely to catalogue what exists, but to consider the ethics of annotation. The Earth's book is enormous and fragile. Many folios are already torn. Yet much can still be preserved, clarified, and intentionally left intact for those who follow. The threefold counsel, read with humility, record carefully, and leave books for the future, is not an inventory of dos and don'ts so much as a mode of being, a cultivation of patient attention, disciplined restraint, and intergenerational generosity. If the planet continues to be both author and editor, then the quality of future readers' accounts will depend on the choices made now. The handwriting humanity appends to the margins will be legible to whatever intelligences come later, be they descendants of the present biosphere or entirely different modes of perception, if and only if those choices respect the mechanics of preservation, honor the complexity of processes, and accept the moral weight of custody. The library will endure. The question is whether the pages that remain will tell a story of care, curiosity, and restraint, or a series of burnt bookmarks and smudged margins. In the last measure, the recommendation is simple and profound. Treat the earth as a library in which each act of reading carries a responsibility to preserve. That posture, humble, careful, generous, reconciles knowledge with stewardship. It recognizes the smallness of a generation set against eons and, at the same time, the outsized moral significance of decisions made this year, this decade. The library will be read. The choice is what people will have written in its margins when the next reader opens the page.